Yes. Hello. To answer your question, Strange Pen, I did do the Vulkan tutorial a couple of months ago, but I didn't get very far, and I basically remember nothing, so we're gonna start over. Hello, chat. Hello, Code Green. Today I decided that rather than working, I'm gonna do Vulkan stuff because I need a break. I don't know. I've just been super burnt out on work for the last couple weeks. So, oh gosh, I just got an eyelash in my eye. Ow. Hold on. Need to get eye drops. One sec. Sorry. Really bad timing. Okay, I'm back. Yeah, ever since I went to Prague last month, my brain has just been completely demolished. I don't really know why, honestly. My work hasn't changed all that much since then, but just ever since then, my brain has been completely destroyed. It's weird. Prior roles being UI designer, there are no UIs to design currently, so I've just been doing QA. Oh, man. Okay, so we're going to be following the Vulkan tutorial, but there is one thing that I am going to do differently. I am going to use the Vulkan C++ API instead of the C API because RAII and all the other things. So we're gonna try that out. I usually prefer to write my projects in C instead of C++, but considering how complicated Vulkan's gonna be, I think I need the memory management of C++. So yeah, we're gonna do that. We're just gonna start. Okay, let's see if I can remember how to write a Mason project in my nope, I don't. I already forgot. Let's do SDL OSU. There we go. Vulkan tutorial, C++, or is it CPP? I can't remember. We don't need any of these yet, but we would like SDL3. Rate the difficulty of this in terms of planets when he's done. On a scale of novice to Gleba, it's probably gonna be Gleba. Let's be honest. Okay, I also need my just file. Gosh, there's a lot of boilerplate. Just file, editor config, Clang format, and my CAC-RC. Clang format, that looks fine. Yep, that looks good. I am also gonna copy this over for my vertex and fragment shaders, I think. I've come to realize that I like 4-space indents more than 2-space indents. So we're gonna try that out. Okay, cool. We're gonna make our Meson file in here as well. Just gonna shamelessly steal that from my OSU project as well. Yep. There we go. Okay, main.cpp doesn't exist. We're not on C++ 23. C S to D, VP, S to D equals C++ 23, I think that's how you do it. CPSD equals C++ 23, yeah, that's correct. But what is this? Current directory is not a Meson build directory. Hello world, there we go, awesome. Okay. But this is not working. Editor config? Oh, there we go. Okay, we are also going to echo a git ignore into our cache there as well. That is a fun fact, by the way. If you have a .gitignore in a subdirectory and you just set it to star, then it will ignore everything in that directory, including the directory itself. So what Meson does, the Meson build system does, is it puts its own gitignore in here so that no matter what if you're like Meson set up build 2, it'll automatically ignore build 2 in Git. And also in HG, apparently. Okay, but let's Vulkan tutorial. And then our just file, Vulkan tutorial. There we go. Just run. Awesome. All right. All right, cool. Now we have our 4-space indents as well. Please let me know if the text is big enough. I tried doing a 1.5 scale, but I feel like that's too large, so I'm trying 2.5. Hello, Mars. Was Vulkan? Yeah, so as Code Green mentioned, Vulkan is a graphics API. So if you do something like, for example, let's just run Factorio because that's the best example here. So Factorio is run on OpenGL, which is a much older but also much easier to use graphics API. Vulkan is much newer. It came out in 2016, so it's like 9 years old instead of like 40 years old. I feel like that music's a bit loud. I'm gonna turn it down a little. Oh, actually, it's just loud in my monitoring headphones. Yeah, Vulkan is much newer, but it also means it's much more difficult because it gives you a lot more control. So we are going to see what we can do. 2-space indent is a bit too tight. I see the point in 3 since 4 can feel a bit much, but also cursed. Yeah, 3-space indents. Dang it, what's that joke language? Dang it, what was it? A language with 3-space indents. Joke language with 3-space indents. Dagnabbit. There was some really funny like TypeScript SOlang that was solang.org doesn't exist for Gart. SOlangs, thank you. It still doesn't exist. SOlangs. It's just solangs.org without the dash in it. Yeah, I don't know what it is anymore, but maybe I'll find it later. Okay, anyway, let's get going. Okay, so introduction. This tutorial will teach you the basics of using the Vulkan Graphics and Compute API. Vulkan is a new API by the Kronos Group, known for OpenGL, that provides a much better abstraction for modern graphics cards. This new interface allows you to better describe what your application tends to do, which can lead to better performance and less surprising driver behavior compared to existing APIs like OpenGL and 3D. The ideas behind Vulkan are similar to those of DirectX 12 and Metal, but Vulkan has the advantage of being fully cross-platform and allows you to develop for Windows, Linux, and Android at the same time. But notably not Mac OS, because Apple have sticks shoved up their butts and decided to do their own thing instead. However, the price you pay for these benefits is that you have to work with a significantly more verbose API. Okay, we don't need to read all of this, but I do know that Vulkan requires you, like OpenGL basically gives you a global state, and then you modify that state. But Vulkan, basically, you manage the state yourself, which is a lot better, but it's also a lot more difficult. Okay. Vulkan's not for everyone. Oh man, it's targeted at programmers who are enthusiastic about high-performance computer graphics and are willing to put some work in. If you are more interested in game development rather than computer graphics, then you may wish to stick to OpenGL or Direct 3D. Well, I'm gonna ignore you and go on anyway. Okay, so we do have a graphics card that's compatible with Vulkan. We do have experience with C++. We do have a compiler with decent support of C++ 17, because we're using C++ 23, because I can't use it at work, so I use it in side projects because it's fun. Some existing experience with 3D computer graphics. I did the OpenGL tutorial. In fact, I can show you. Make setup. Make run. Here's my OpenGL tutorial that I did. I don't remember how this works at all, but I did it. I also added some of my own features like this IamGUI debug thing. I can turn off VSync and it goes at 1000 hertz. I can pause. I can turn off the cube rotation. I can change the color of the lighting. I can change the clear color as well. Woo! Yeah, that was my OpenGL tutorial. It gave me, it taught me how to do Phong shading. So you have like the specular highlights on the metal bits of this box, and you have the diffuse and ambient. There's diffuse lighting, there's specular lighting, and then there's a third one that I can't remember right now. Direct lighting, like where it bounces off at the angle of incidence is equal to the angle of reflection. That sort of lighting. What C++ version is Factorio stuck at? We're actually on 20, just 20. There's nothing after that, just 20. C++ 20 is pretty nice. Like 1.1 was on 17, 2.0 was on 20, but we can't use things like std format because std format isn't supported on macOS yet fully. So no, we're actually pretty modern, but we can't use like std println or anything because we're still on 20. But that doesn't matter anyway because we use Trio instead of the standard printf. So we're doing a separate thing anyway. Okay. You can use C instead of C++ if you want, but you have to use a different linear algebra library, and you'll be on your own in terms of code structuring. All right, so we're going to be using GLM as well, I assume. So this tutorial is going to teach us how to use the C API, but like I said before, we're going to be using the C++ API instead. I think it'll make things slightly easier, but we are going to disable exceptions because exceptions are literally Satan, so we're going to not do that. How hard has Vulkan been so far? Well, we haven't even started yet. We've written a Hello World program, and that's it. Okay. After you've gone through the ritual of drawing your very first Vulkan-powered triangle on screen, we'll start expanding the program to include linear transformations, textures, and 3D models. If you've played with the graphics APIs before, then you'll know there could be a lot of steps until the first geometry shows up on screen. There are many of these initial steps in Vulkan, but you'll see that each of the individual steps is easy to understand and does not feel redundant. It is also important to keep in mind that once you have the boring-looking triangle, drawing fully textured 3D models does not take that much extra work. Each step beyond that point is much more rewarding. Okay, so getting your first triangle is ridiculous, but after that it'll be easier, I guess? Okay, let's go. Production overview. Okay, we probably don't need to do all of this. Just like previous graphics APIs, Vulkan is designed to be cross-platform abstraction, except for Apple. The problem with most of these APIs is that in the era in which they were designed, featured graphics hardware that was mostly limited to configurable fixed functionality. Right. This is something I learned recently. Before the Wii U, like if you're looking at Nintendo consoles, for example, all Nintendo consoles up until the Wii U had fixed function pipelines for their GPUs. So you couldn't really make programmable shaders whatsoever. You were stuck with what the GPU had programmed in it already. That's why a lot of N64 games, for example, look really similar to each other, because they all used the same shaders or the same fixed function pipelines. It wasn't until the Wii U that Nintendo finally graduated to fully programmable shaders. Programmers had to provide the vertex data in a standard format, and they were at the mercy of the GPU manufacturers with regard to lighting, and shading options. As graphics card architecture matured, they started offering more and more programmable functionality. All this new functionality had to be integrated with the existing APIs somehow. This resulted in less than ideal abstractions and a lot of guesswork on the graphics driver's side to map the programmer's intent to the modern graphics architectures. Yeah, that's the reason why I really want to learn Vulkan, is because I freaking hate OpenGL's API. Let's see if I can find an example. Graphics. Like, there's a bunch of these GL functions that have really weird names, like GL gen textures, GL bind texture. I mean, those are fine, but like GL text image 2D. None of these have documentation. You have to go to like open or docs.gl, I think it is. And then you have to search for the thing, your TL text image 2D. And then you have to select the version of OpenGL that you're using, and then it'll give you some documentation. But like, it's not in line in the editor. You have to go to a website. Like, I freaking hate it. It's just a mess, dude. That's why I really want to learn Vulkan, because Vulkan has a much more sensible API from what I've seen so far. Okay. That's why there are so many driver updates for improving the performance in games, sometimes by significant margins. Because of the complexity of these drivers, application developers also need to deal with inconsistencies between vendors, like the syntax that is accepted for shaders. Hold on, I haven't been reading chat. My bad. Does Vulkan have shaded programs like OpenGL? Yeah, so Vulkan, it's about to get into that. Vulkan uses a shader bytecode called SPIR-V. So when you write your shaders, like, for example, this fragment shader, this is in GLSL, but then you'll compile this into SPIR-V, which is a bytecode format. So my editor can't display that, obviously, because it's binary. And then Vulkan will consume this and then use that to display something, or use that to do the shader. The advantage of that is you no longer have vendor-specific implementations of GLSL, for example. You can use any front end for GLSL you want, and then it compiles it all to a very consistent format that will work across anything that uses Vulkan, theoretically. Aside from these new features, the past decade also saw an influx of mobile devices with powerful graphics hardware. These mobile GPUs have different architectures based on their energy and space requirements. One such example is tiled rendering, which would benefit from improved performance by offering the programmer more control over this functionality. Just display the byte-coded file as hex to confuse everyone. Yeah, that would be if I had a nice hex editor. Actually, I do. I am hex. This is the best hex editor ever, but it doesn't support Wayland, so it's blurry as trash. Here's our vertex shader. Isn't that beautiful? I am hex is nice because workspace diff. I use this for debugging desyncs in Factorio. So you can load two different DAT files, for example. So I can, and then it'll give me the diff between them so I can see exactly what is different between the two save files. Isn't XXD already installed by default? XXD is trash. It doesn't have like any features. If I was working on Factorio from the beginning, I could have also made an imhex like format file for the save files based on like serialization data and stuff in the game engine. It would allow me to do syntax highlighting for the hex data in the save file, which would have been awesome. Okay. Yes, so Vulkan's designed from scratch, modern architectures, it reduces overhead, yada, yada, yada. Okay. What it takes to draw a triangle. Instance and physical device selection. Right, so in Vulkan, you have to actually like enumerate your physical devices and select them. Logical device and queue families. You select your physical device, you create a logical device, and then you have to create queue families so that you can submit commands to a queue instead of just modifying global state like in OpenGL. Window surface and swap chain, you have to also set that up yourself. You don't just get automatic or double buffering or triple buffering like OpenGL. You have to actually set it up yourself. I should actually probably read some of these. Create a VK device. You describe which VK physical device features you'll be using. We're not going to be using multi-viewport rendering or 64-bit floats, so we're fine. Do asynchronously executed by submitting them to a VK queue. Right, so that's a thing. In OpenGL, I think everything is synchronous. Don't quote me on this, but I'm pretty sure if you like call like bind buffer, it'll actually block until that's done. Whereas in Vulkan, you assemble a queue, and then you add things to that queue, and then you submit all of your commands at once. So it only blocks while it's sending, and then it'll execute them in asynchronously. I think. Don't quote me on that though. But you can create multiple queues. You can add to them across multiple threads, so you can make it a lot more efficient. Whereas in OpenGL, you have to do most OpenGL operations on the render thread, which kind of freaking sucks. So there could be separate queue families for graphics, compute, and memory transfer operations. The availability of queue families could also be used as a distinguishing factor in physical device selection. It's possible for a device with Vulkan support to not offer any graphics functionality. However, all graphics cards with Vulkan support today will generally support all queue operations that we're interested in. And this is something interesting as well. So Wayland right now on Linux is suffering a lot because of you have the core Wayland protocol, which is just these things. So it's not all that much. But then you have all of these extensions that are all optional. So you have to query to make sure that whatever you're using supports all the extensions that you want, and a lot of things don't. Like for example, Layer Shell. Wayland Root's Layer Shell is supported by pretty much everything except for GNOME. And then there's FIFO, which is supported by GNOME and KWin, but not much else. And the other one I wanted to look at was a top-level tag. Top-level tag is only implemented by KWin right now. So, like, yeah, you have to check for all these. But I found out that in Vulkan, you do have this same thing where you have a sort of small core, and then you have a zillion extensions. But the difference is you have Vulkan standards. So, for example, you have like Vulkan 1.0, Vulkan 1.1, 1.2, etc. And those all specify that if you are Vulkan 1.2 compliant, then you implement all of these extensions. So it makes it a little easier. So you'll know if a device advertises itself as supporting Vulkan 1.2, then it supports all of those extensions as well. I think that's a better way to do it. Okay. Window surface and swap chain. Unless you're only interested in off-screen rendering, you'll need to create a window, so you can use GLFW or SDL. We're going to be using SDL. They're going to be using GLFW, but we're going to be using SDL, so that'll be interesting. Debo, we are learning Vulkan. Also, thanks for the hydrate. I needed it. Window surface and a swap chain. KHR postfix, which means that these objects are part of a Vulkan extension. Okay. So if it has KHR in it, then it's an extension. Why is it not called EXT or something? What does KHR stand for? I need to use the standardized Windows System Interface extension to interact with the window manager. Surface is a cross-platform abstraction over Windows to render to, and is generally instantiated by providing a reference to the native window handle. For example, oh dang it, I know what this means. Handle window on Windows. Luckily, the GLFW library has built-in function to deal with platform-specific details of this. Okay, so we're actually going to start initializing SDL and garbage. Okay, and I am gonna shamelessly steal some stuff as well from a previous project. I'm gonna steal. These are 3 functions that I use all the time. SDL safe call, SDL safe assign, and panic, which also includes SDL ASPrintf. There we go. So now I can just do SDL safe call, SDL init. And this will automatically abort and give me a pop-up if anything goes wrong. So that'll be much nicer. But the not nice part of this is I don't know how to use it with unique pointer, because what I would do in C is I'd do SDL window, and then SDL safe assign window, SDL create window. 800, 600, SDL window, high pixel density, window Vulkan, like that. But I can't do that because I can't assign. All right, hold on, that's not it. Oh, title, Vulkan tutorial. There we go. That works. But if I try to do that with unique pointer, I can't, because I can't assign that to unique pointer. Window pointer, and then window.reset stood move no pointer, something like that. That's really stupid though. That is very stupid. I'll just do it manually. So we'll do window.reset SDL create window with all these things. If not window, panic, create window failed. Call me Golang if error not equal nil. Okay. So now you need an async runtime to handle those queues? No, you can just do it across multiple threads. Invalid application of size of to an incomplete type SDL window. What? Is it because it's an opaque object? Can I not put that in a unique pointer? Why am I using C++, dude? Do we really want to use C++? Should I go back to C? No, because Vulkan's so complicated. I really want RAII, so... Okay, fine. We won't use unique pointer then. Okay, there we go. So we're creating our window. Bool quit equals false. Here's baby's first game loop. Okay, so if I do that, then it'll just heckin' die, or it won't do anything. There's no window because we haven't initialized it yet. You would need to provide a destructor for unique pointer. Stood unique pointer, SDL window, void, SDL window. Oh, that makes sense. Whatever. I'll just handle this manually because that sounds like annoying. Okay. Image views and frame buffers. Render passes, graphics pipeline. Okay, well we'll figure this out. We'll get there. Coding conventions. All the Vulkan functions, enumerations, and structure defined in the Vulkan.h header, which is included in the Vulkan SDK developed by Linergy. So this is like my favorite thing about Vulkan. You just include the header, and then you get the stuff. You don't need to use a binding generator or nothing. You just include the frickin' header, and it just frickin' works. And in our case, we can just include the HPP header. We want to use the HPP library instead of the H library. Right, so you would usually have a create info, then you'd populate it, and then you would create XX and check if the result is not equal to VK success. Then you print to C error. I freaking hate the IO streams interface, dude. This is like the worst, the least readable code I've ever seen. Malform Barracuda, thanks. This reminded me that I hate C++, so maybe we'll end up going back to C if I get too annoyed with C++. Okay. Almost all functions return a VK result as either VK success or an error code. But we are using this instead. So I want to disable... I would like to disable exceptions, please. Factorio is in C++. Yes, Barracuda, I know about println. Vulkan, HPP, no exceptions. Okay, there we go. So now we will be able to do that. Okay, so we'll figure that out. Validation layers. Yeah, this is the other reason why Vulkan's awesome, because instead of things just breaking, you can install validation layers into every step, and then it'll give you errors and tell you what's going on if you do something wrong. Okay. Setting up development environment, I already did this. Linux, Vulkan packages, yeah, I got those already. GLFW, GLM, we should probably add that to our dependencies. Okay, we found GLM, we're good. What about Vulkan? We need to do that as well. Yes, cool. Awesome, so now we have GLM, STL3, and Vulkan. We're probably gonna need STL3 image as well, so we're gonna keep that around. We'll just add it right now, I guess. Yep, we're good. Because when we do textures, we're probably gonna want that. Okay, git init. Selected item is not a branch, what? I kind of like the trunk name. It's kind of funny, so we're gonna use it. Good, we good, yeah. Cool. Okay, so, render stuffs. GLM, shader compiler, we do have GLSLC. We also have GLSL Lang. I think I'm gonna try, well no, we're gonna use GLSL because that's what the Vulkan tutorial uses, but I really want to learn HLSL because apparently it's better. Both are fully supported, so, but yeah, we are gonna use GLSLC because it's a lot easier to use. So we're gonna add to our just file. Build shaders. GLSLC shaders slash anything.frag. I think that's how you use it. We'll find out. Okay. WGSL, the best shader language. You know, actually, SDL shader language. SDL is making their own shader language. That would be cross-platform and would just work with SDL GPU. I think that's actually super cool, but it's not ready yet. SDL is just like, you'll be able to use SDL GPU, you'll be able to use SDL shader language, and then it'll compile to all 3 native platforms like Metal, DirectX, and Vulkan. So, yeah, that'll be interesting. But we're just gonna do Vulkan because Vulkan does give you cross-platformness. So, like, I like the idea of SDL GPU because it's like a higher level wrapper over Vulkan. In fact, just yesterday, the reason why I wanted to do this is because yesterday I was messing with SDL GPU. I made my own triangle. This is on SDL GPU, but I wanted to learn Vulkan directly because I feel like that'll be more useful for my career. So our goal is to make this in Vulkan directly. Such a pretty triangle, thank you. Okay, shader compiler. Setting up makefile. We already did that. We're using Meson. Meson is the superior build system. Everyone should be using it. Teammate can get out of here. Fast build can get out of here. Meson is where it's at. Yeah. All right, macOS. Most important component you'll need for developing Vulkan is the SDK. Wait, macOS. These instructions will assume you're using Xcode. So keep in mind that you'll need the latest macOS version 10.11. Device to support the Metal API. Right, so that's what I was saying earlier. Like, I like the idea of SDL GPU, but the reality is that Vulkan is already like completely cross-platform, including on macOS if you use Molten VK. And that basically is a translation layer from Vulkan to Metal. And it works pretty well from what I've heard. So just write your games in Vulkan and then you'll be fine. Maybe not for like game consoles. I do know that the Nintendo Switch supports Vulkan natively, which is really freaking based. But I also know that Xbox basically makes you use DirectX and PlayStation has their own proprietary thing. So yeah. Okay, GLFW, GLM. Okay, setting up Xcode. We don't need to do that. Yada. Okay. We got GLM, we got Vulkan, we got STL3. We're good. Base code, general structure. Okay. Okay. Putting everything into a class. Classic. Okay. We'll probably just follow this for now. Just for the ease of following the tutorial, even though I don't particularly love it. In fact, we're going to throw these into another file as well. There we go. Panic not declared in the scope, you mean util panic, okay. Man, why does C++ take so much longer to compile, dude? C is like so fast. Okay, there we go. Do C++ modules? No thanks. I tried that before and it does not work. Okay, class, I guess we'll just do it this way because that's what the tutorial wants us to do. It's kind of gross, but class game, we're just gonna call it game. I like that more. Init Vulkan, main loop. Yep. Well, no, I hate that. No, we're not doing that. Okay. Init Vulkan, main loop, cleanup. We're making this, we'll probably make it a singleton class so that we can throw this on here. But don't use Vulkan HPP, it's really heavy. Holy crap, you're right. That went way faster. Holy frick. Vulkan HPP is so slow. Chat, do I use C? Do I go to C instead? I really want to go back to C. I freaking hate C++. I think I go to C. Go C. Let's go C. Okay, so let's, he's on C, thank you. C, std equals C23, thank you. But we're gonna have to use CGLM instead of GLM, that's fine. Do we have CGLM? No. Oh, I miss Alpine Linux. I've been using Alpine Linux on my laptop for the last week and a half, and it is so good. Okay, no matches found. Wrap install CGLM. I know it's in Meson wraps. Oops. There we go. Now that should just work. Yes. Okay, util.h. Okay, we're good there. Get out of here, game. Okay, util.c. We get rid of the main namespace. And we get rid of that namespace, and then we're good. Ah, so much cleaner. Oh, wait, hold on. Get rid of this. There we go. Oh, it's so much faster. Okay. APK add everything. True. Okay, so now we're back in C. I'm so much more comfortable in C. Okay. Because like in C++, I feel like if I'm doing something that's not trivial, I have to look things up like every 2 seconds, even though I've been using it for 2 years. Whereas in C, I have like pretty much the whole language in my head. So while it is less easy to program in, I don't have to look things up nearly as often. There we go. Okay. Still no Vulkan header though. Include vulkan.h. Oh, wait. Oh, yeah. Out of here. Include vulkan/vulkan.h. Ha! See, look how much faster that is. Even with the Vulkan header. Okay. Cool. So now we have our main loop. Speed. We have our main loop, init Vulkan, main loop, cleanup, try app.run. See, like, I freaking hate exceptions. Exceptions are the worst thing ever made. I hate them. I watched a video on data-oriented design a couple months ago by someone who makes Insomniac Games, I think it was, an Insomniac Games engine developer, and he was like, "Okay, so how do we make our games fast? First thing we do is we don't use the standard library and we don't use exceptions." I'm like, that is so based. No STD, no exceptions. Oh man. Okay. Factorio uses exceptions all over the place, and it's a freaking mess. Okay. Now we're good there. You know what? We're just gonna make a window, just a cheeky little window. Now we should have a window. Window! Really that slow? Yes, exceptions are horrendously slow. Yes, and like, as much as I've poo-pooed on Rust in the last year or two, Rust's result is like the best thing ever, dude. Although, actually, no, that's wrong. Hair has the best error handling I've ever seen. Do I still have Kilo in here? No. But I wrote a text editor in Hair, and it was very nice. Hair. This guy. Unfortunately, it's a completely useless language because it only supports free platforms, but it's made by Drew DeVault. And it's actually a really nice language, but like it's just not useful for anything real because it doesn't support multi-threading and doesn't support anything except Linux and FreeBSD, basically. So if I'm writing little Linux tools, I might write them in Hair, but Hair is nice because they have ad hoc tagged unions. So instead of having to create like a specific enum type, like in Rust, where you have your tagged unions inside an enum, you just create a tagged union. Like you'll just do like fn void, or sorry, you'll do fn myfunc param param my type, and then it'll return a tagged union of correct thing or like IO error or even like an FS error. So you can just compose these on the fly, and then you can match over them, and it just makes sense. Like, I love it. Whereas in Rust, you have to like create your own like enum. My result can be like a success thing or an error. STDFS error, however that happens in Rust. But like you have to specifically craft a result type for each individual function if they have different things that they can happen. But in this one, you can just create a type my error void, and then you just return my error as part of the tagged union, and then it just works. Yes, Zig has very similar concepts, but I think the way that Hair does it is better. Okay, anyway. We need to init Vulkan, main loop, cleanup. So let's just write functions for these. Void init Vulkan. And then our main loop is in the main function, because that's where it belongs. Void cleanup. I'll just do that in the main function as well. Cleanup. Okay, we're actually going to do this in the main function as well. So we're going to create our window, then we init Vulkan, main loop. I could use SDL3's main callbacks. That might be nice. But yes, bye-bye, I agree. Rust is not a horrible language, but I really, really freaking hate the Rust evangelists that think that Rust is required for everything, and Rust is always the best choice. Like, I freaking hate it. Okay. Let's not forget our type specifiers, because that's how I like to write my C code. Okay, so First, include the Vulkan header from the LunarG SDK. Okay, we're doing that. Not anymore. There we go. Still accept IOStream. Yeah. Program itself is wrapped into a class where we're still the Vulkan objects as private class members and add functions to instantiate each of them, which will be called from init Vulkan function. Okay, yeah. Resource management. Just like each chunk of memory allocated with malloc requires a call to free, every Vulkan object that we create needs to be explicitly destroyed when we no longer need it. See, that's why I wanted to use C++, because in C++ you can just do that with RAII and it just works and it's great. But doing this in C will be fun. But yeah, we'll see. Basic automatic resource management, providing C++ classes that acquire Vulkan objects in their constructor and release them in their destructor, or by providing a custom deleter to either unique pointer or shared pointer, depending on your ownership requirements. Okay, so yeah, that's what was being said earlier. You can define your own destructor for a unique pointer. That's nice. Vulkan objects are either created directly with functions like vk_create_xxx or allocated through another object of functions like vk_allocate_xxx. After making sure that an object is no longer used anywhere, you need to destroy it with counterparts destroy and free. The parameter for these functions generally vary for different types of objects, but there is one parameter that they all share, pallocator. This is an optional parameter that allows you to specify callbacks for a custom memory allocator. Okay, that's actually really nice. You use stood experimental unique resource. Interesting. Don't you love it when your thumb types a space, even when you don't want it to? Unique resource is a universal RAI wrapper for resource handles that owns and manages a resource through a handle and disposes of that resource when unique resource is destroyed. Okay, that's nice. So it's a generic RAII wrapper. That's cool. Because when I was thinking about doing this yesterday, I was like, oh, I might want to write my own generic RAII wrapper. But then I found the Vulkan HPP is like, oh, I could just do that. But you don't need an allocator for very long. Yeah. We don't really need it. Integrating GLFW. Hold on, I need to. Where's my phone? Over there. One sec. All this thinking is making me sweaty. I need to turn on the AC. Okay. GLFW include Vulkan. Okay. Yeah. Okay, we're already ending the window here, but we're gonna get rid of STL renderer because we're not using that. Right, but we're not using GLFW for Gart. Actually, is that just in here? Frick. There we go. Tests, Vulkan. Yeah, okay, they do, oh, there's also SDL Vulkan. Yeah, but they do it themselves. Okay, yeah. I live without AC with 34 degrees C. Oh gosh, I'm sorry. Geez, look at all these things that you need in a Vulkan context. That's a little crazy. Okay, but I need to create window. Oh, great. STL window Vulkan. Here we go. Well, look at them having common init functions for their thing. Okay, well, let's see if we can figure this out ourselves. So we're gonna SDL Vulkan. Vulkan create surface. Load library. What is this? Dynamically load the Vulkan loader library. This should be called after initializing the video driver before creating any Vulkan windows. The Vulkan loader library is loaded. The default library will be loaded upon creation of the first Vulkan window. Or null. Okay, we can just null this. Okay, so that returns a bool, so we can SDL safe call. And then we'll see. Okay, it worked. Okay, 800 by 600. Ha, I guessed that correctly. Fourth parameter allows you to optionally specify monitor to open the window on. Ha! Not on Wayland. It's a good idea to use constraints instead of hard-coded width and height numbers because we'll be referring to those values a couple times in the future. Okay. Cost, you went 32, T, width. Good. Those actually you went 32. Those are int. Okay, that's fine. I freaking hate it when things in C use int instead of the actual specified types. But it is kind of nice also to just not worry about it sometimes. But yeah, I wish that everything used the like size T and uint32T and garbage instead of just int. I think my least favorite case of this is SDL enumerate directories. Because here, oh shoot, where was it? Hold on. Beatmap reader. There was like an int here, size T. There was a place I was complaining about this. There was something that used an int. Oh well, it doesn't matter. But there was something that used an int that should have been a size T, and it was making me annoyed. Okay. Okay, yep, that's fine. All right, let's create the first Vulkan object. Also, why does it keep doing that? I already have it included in SDL.h. Like, you don't need to do it again. And I tried Clang D, header insertion never, and yet it still does it. That's annoying. Creating an instance, okay. Init Vulkan create instance, okay. Create Vulkan create VK instance. Let's see if we need to do this. Okay, so we keep a struct VK instance. VK instance. Oh. Oh. I hate it. I want to use struct. Okay, so now we can create instance. With first fill in a struct with some information about our application. Okay, so we have VK application info equals, okay, application version. Does that matter? It's just a uint32. What is this? Oh, just, that's, okay. VK make version is deprecated. Use VK make API version should be used instead. Okay, so this tutorial uses deprecated stuff. Variant major minor patch. 0? Okay, so that is another, that's weird. You have to specify the type even though it's already specified here. That's weird. I guess that's probably because it, if I had to guess, it probably passed these around as void pointers, and then it has to determine, it's like a tagged union pretty much, like this is the tag. That makes sense. So this is probably the first, yeah, it is. Okay, so that's exactly what it is. So if you pass in a struct, it'll be a void pointer, but then it casts it to some generic type that always specifies the S type as the first member, and then it uses that as a tag to determine what the rest of it is, and then it casts the pointer to that. Okay, that makes sense. So we're gonna put that first. Dot p application name equals Vulkan tutorial. Okay, application version. That is void pointer and pnext fields. It's done for extensions. I see. Cool. In .p engine name equals no engine. Ha. How about we do a rye engine? Ha. Engine version. We're just gonna use a VK make version, even though it's deprecated. Dot API version equals VK API version 1.0. Okay, yeah. So now we're only using API version 1. Okay, as mentioned before, many structs in Vulkan require you to explicitly specify the type in the S-type member. This is also one of the many structs with a pnext member that can point to extension information in the future. We're using the value initialization here to leave as null pointer. Okay, so yeah, pnext is like, it's like a linked list. You can link it to another struct that has more info. Okay, so now we can create info. A lot of information in this Vulkan is passed through structs instead of function parameters, and we'll have to fill in one more struct to provide sufficient information for creating an instance. The next struct is not optional and tells the Vulkan driver which global extensions and validation layers we want to use. Global here means that they apply to the entire program and not a specific device, which will become clear in the next few chapters. Okay, so there is some global state. I guess that makes sense. P application info. Oh, that's vInstance create info. Okay. App info. Okay, so you put the app info into an instance info, and then you add. First two parameters straightforward. The next two layers specify the desired global extensions. Okay, so what other are in here? Step API version, edge version, pengine name. Oh wait, that's app info. Dot. Okay, here we go. Enabled extension count, enabled layer count, PP enabled extension names, PP enabled layer names. Okay, so they use the convention where they tell you the type of the thing in the name, which is kind of nice, but also kind of redundant. I don't really love that. But PP is funny. Okay. So we have glfw extension count, glfw extensions. Okay. Is there an SDL Vulkan get instance extensions? Did the Vulkan instance extensions needed for VK create instance? Okay, cool. So this is called after load library, which is fine. Yep, we're doing that already. Okay. It says const car const point. Oh, I hate that. Const car const extensions. Single argument count was not specified. Okay, so we have a. Is this actually in a uint32? Yes. Okay, so that is a const array of const car. I love C. Okay, I'll just do it like that. Oh, nope, I can't. Cool. Instance info dot enabled extension count equals extension count. Is that actually uint32? Yes. Instance. Oh, thank you, VK API for actually using the type definitions. Like we're in 1999. Awesome. But I'm pretty sure they also still have VK bool. I thought I saw VK bool somewhere. VK bool. Yes. Why? Just use bool. Bool. You're in C99. Come on. Okay. TP enable extension names equals extensions. Okay, I usually like to put the array first and then the count after, so we're gonna do that. Okay. Last two members of the struct determine global validation layers. We'll talk about these more in depth in the next chapter, so we'll leave these empty. Okay, we can just leave that. Now specified everything that Vulkan needs. Okay, so now VK result, VK create instance, create info, or instance info. Null pointer, or null instance. Why? Oh, fine. If we're gonna do it that way, then we'll do it that way everywhere. That's sad. Okay. 4-byte bool. Oh, wait. Are you telling me that bool is 8 bytes? Wait. Bool is underscore bool. And underscore bool is bool. Huh? Where? Okay. A C99, how large is bool? Oh. Size of bool mostly returns 1, but not on all platforms. That's 8 bits. What are you talking about? It's 1 byte. It makes no sense to have an 8-byte bool. But why do you need a 4-byte bool? Maybe it's for padding reasons? I don't know. Okay, so we can probably result... What does VK result? Okay, we have a gazillion results. Okay. hpix poke. How you doing? So we're gonna add another util function, or a util macro. Define VK call func name that. If func name parameter is not equal to VK success. Okay, pointer destructive creation info, pointer custom allocator callbacks. Okay, is there like a VK get error or something? Okay, Vulkan, get error string. Vulkan VK enum string helper. String VK result. Okay, that's a weird way to do it. Oh, that's not there. Okay, well let's see if it already exists. String Vulkan. No. Well, Vulkan enums? Well, we'll just print the number for now. Okay, so VK call, VK create instance with all those things. And then util.h, panic. Okay, that should do it. Selected expression. Oh, VA args. That'll integer to pointer conversion, passing VK result to parameter of type const car. Oh. Also, I like how Clang doesn't format my macros for me. Funny. Okay. Oh, all right. No, it's fine. All right. Panic. Also, why are these 2 space indents? Yep. And in Factorio, we just have 2 string global, and it just converts anything to a string, and it's awesome. I know I have. Do I just have to AS print fprintf? No, I'm just gonna create a buffer, and then R4096 buff. That's like super huge. Freaking why is C like this? Array should be part of the type. Like, that's also why I do pointers like this instead of like this. Because the pointer is part of the type, not the value. Okay, SDL fprintf. Or sorry, it's just print. Wait, don't tell me. Oh, it is fprintf. Buff. And then this is a, what is the underlying type of EK result? It doesn't have one. Just try %d. Yeah, that's not it. Oh, what is it? What is it? Is it just sprintf? Yes. Yes, it is sprintf. Okay. Buff. Okay, well now that we've done that here, we need to put that into the macro. Okay, we're gonna make this like 64. It doesn't need to be that large. Okay, so now we will do I promise this will be worth it. Just trust me. VK call, VK create instance, instance info null, and instance. There we go. That seems to work. Awesome. Yeah, Fagart, you're right. I agree. About if you need padding, just make a padding variable. Okay, cool. VK call was there. And we're good. All right, so I should have an instance now. Okay, nothing happened. Awesome. We're good. It worked. Yay, okay. Thank you for extension support. If you look at VK create instance documentation, you'll see that one of the possible error codes is VK error extension not present. We could simply specify the extensions we require and terminate if that error code comes back. This makes sense for essential extensions like the Windows system interface, but what if we want to check for optional functionality? To retrieve a list of supported extensions before creating an instance, there's the VK enumerate instance extension properties function. Okay. Thank you for the follow, Systemic. Appreciate you. Takes a pointer to a variable that stores the number of extensions and an array of VK extension properties to store details of the extensions. It also takes an optional first parameter that allows us to filter extensions by a specific validation layer, which we'll ignore for now. That's interesting. Okay, so we're probably going to end up not using VK call in this case because we're going to need to actually check against the return value, the result. But hey, live and let learn. Okay, so we extension count equals 0. Okay, enumerate instance extension properties. Okay, so what are those? What are those? So we have player name. Wait, oh, P layer name, not player name. I was about to say that was a typo. Okay, P layer name, P property count, P properties. Okay, I see. So we get the extension count first. Okay, so we get that first, and then we can allocate, we have to allocate an array that can hold this. So they did it with a stood vector, but we need to do it with an array. Okay, so we're gonna, what is the type of that? VK extension properties props alloc. All right, we're gonna calloc. Oh no, we're calloc available extension count, size of VK extension properties. Easy. Really? Okay. And then we do it again, but this time we props. I'm probably gonna regret doing this and see if we need to resize any arrays. I'm gonna have to write my own array vector wrapper, and it's gonna. Maybe I'll just bring an STB array. STB array. Do they have a list? No. Well, I thought they did. Guess we'll just do it ourselves. Finally, we can query the extension details. Okay. Yeah, so we grab the available extensions. This is gonna reassign that again. Probably don't need to do that. That's fine. Yeah, put s, or no, printf. I guess I'll use a tab. Okay. So now we have all these things. You can add this code to the create instance function if you'd like to provide some details about the Vulkan support. As a challenge, try to create a function that checks if all the extensions returned by that are included in the supported extensions list. Okay, well, let's do that. So we have the SDL extensions. Yeah, we're gonna iterate over the available extensions. And then maybe we can use SDL properties. You can use Vulkan info command. Oh, that's nice. Hey, frog protocols. Okay, Chronos validation. Wow. Am I gonna dox my GPU information? That's a lot of info. 3,839 lines. Crazy. Oh, I do have Vulkan 1.4 support. Nice. Mesa is based. Okay. Right, so we want to do this. We could make a hash map. We are using SDL, so we can just use SDL properties as hash maps, because that's basically what it is. SDL extensions map. Create properties. Okay, SDL set string property. SDL extensions map. And then we can just could you stop auto-including things, KlingD? Thank you. Okay, we're gonna set those to false. So now if we do SDL has property, SDL extensions map. Wait, oh, wait. No. If SDL has property, then we SDL set property. Okay, that should do it. And then we do SDL enumerate properties. Oh, that's annoying. We have to do it with a callback. Can I define that in here? Void CB. So that does Function definition is not allowed here. Dang it. Would have been too good. Check SDL or check true callback. Sure. Oh, this is annoying. In C++, this would be just for thing in map. But you could in C++ with a typer lambda. Yeah, you're right. But I need more experience with C, so that's what we're doing. Well, I guess I need more experience with C++ because the reason I'm using C is because C++ is hard. Yeah. But I like C. C is fun. Wouldn't it be truth more appropriate since you're checking for Boolean, not just true? Check truthy. Maybe. I don't know. Well, I'm checking true callback. Okay. So we have props if SDL get Boolean property. What happens if you use SDL get property type? So that you can't return from there because that's not how that works. So we do SDL extensions map. Check true callback. And then the user data will be bool all bool all true equals true. We'll pass that as a pointer, and then we'll do bool user data equals false. Love typecasting in C, yeah. Okay, so after we enumerate that, if not all true, panic device does not support all SDL extensions. All extensions required by SDL. Okay, so we will test this first by doing this. Okay, that worked fine. But then we will put a SDL add Boolean, set Boolean property, SDL extensions map, my extension, false. Then it should crash. Yep. You like my panic macro? Or, yeah, my panic function? So there would be a description here, but there isn't really that. Okay, so now that we've done this, I really hate this. This is not a good way to do this. So we're going to delete everything we just did. and do it a different way. Because that's the C++ way. If I wanted to do that, I'd just throw them all into a set and then or a map and then do it that way. But since the number required is probably going to be kind of small, we can probably just oh no, but we do need to keep track of. No, it does need to be the other way. Oh, that's annoying. I mean, that's gonna be slow. That's fine. Oh wait, no, there's a much easier way to do this. We add all of these to a map, and then we can check for those. By the way, C++ and Git Master Clang already supports Veretic structured bindings, which is a really cool addition to the language. Ooh, it's nice. Okay, yeah, so actually we do it this way. SDL properties ID available extensions map. And then when we do this here, we do SDL set Boolean property available extensions map extension name true. And then we iterate all of the ones required by SDL, and then we do if SDL get Boolean property available extensions map required extension name false. If not, then we panic. Device does not support required SDL extensions. Required extension. There, done. None of this enumeration garbage. It'll be much faster. Okay, and now, if we want to test this, then we would need to do +1, and then do available. Sorry. Up here. Oh, no, that's const, frick. Okay, we can't really test it then. We're going to assume that it works, but this is much nicer because then we don't have we still have the lookup table, so it'll be fairly fast. But we don't need any of this callback nonsense. That's much better. Also, get rid of that. Thank you. Awesome. Okay, so we're an hour and 37 minutes in, and we're still just initializing Vulkan. Yes, all required, thank you. Device does not support required SDL extension, and then it'll print the name. One week later. Okay, but yeah, this is a much better way to do it. And then let's not forget to SDL destroy properties, available extensions map. We might end up wanting that later, so we might keep that. Okay, but now in the cleanup, we want to VK destroy instance. Instance. Null. Okay, but this also seems kind of redundant because if it doesn't support all of the extensions, then it's gonna fail to create the instance. Isn't that right? Like, because we passed the SDL extensions in here, and then Vulkan should automatically return a failed result if we don't support all the extensions. So all this is freaking useless then, right? Am I crazy? I mean, we'll keep this for now, but we'll add it to do. So we'll fail to create the instance if check for extension before creating instance. Right. Does this require the instance? No. No. Yeah, you're right. That's the solution. Yeah, Barracuda, you're right. Yeah, I should have realized that. Okay, so the VK call is still going to be useful here then. But I really wish I could get that enum. Vulkan tools? Oh, it's already installed. Vulkan utility libraries devel? Yeah, let's try that. Come on, DNF, go faster. Thank you. Yes, there we go. That was the package we needed. Also, why is that there? Okay, so we can now, in our VK call, well, actually we could do this here. VK call, we can go here. Instead of doing this, we can do string. Oh wait, no, we do need to include it here. String VK result VK call. I think that's it. Yeah, maybe. Yes. Awesome, easy. So now it'll print the function that failed and the VK result. Okay, so let's try to make this fail. Just get out of here and see if it works. Oh. Huh? Oh, yeah. Initialize. There we go. Oh, it didn't actually crash. What if we pass the pointer without the count? It still didn't crash. Vulkan, can you crash? Vulkan? Please? All I want is for you to break so I can test my error handling. How can I do this? Flags equals. It's still not. Please. Pnext equals pointer to available extensions map. Sure. Okay, now it's just segfaulting. I'm failing to fail. Okay, what if we pass the wrong type? Instance, loader instance create info. How about that? Nope. Okay, maybe it is failing and our VK call sucks. No, it's definitely working. Okay, well, we'll figure this out later. Okay, cleaning up. You can destroy instance. Yeah. Okay, cool. Okay, before continuing to the more complex steps after instance creation, it's time to evaluate our debugging options by checking out validation layers. It didn't take a moment to initialize? No, it didn't. That's just Cocoon being stupid. When I run C programs in Cocoon, it doesn't flush immediately. It doesn't flush until I hit Control C, and I don't know why. But if I run it in an actual terminal, then you'll see it does it immediately. If I do this, then it'll do that. But if I do it here, then it'll do it immediately. Oh, excuse me. Okay, cool. So we've initialized Vulkan. We're 2 hours in, and we've initialized Vulkan. Awesome. Okay. What are validation layers? The Vulkan API is designed around the idea of minimal driver overhead, and one of the manifestations of that goal is that there are very limited error checking in the API by default. Even mistakes as simple as setting enumerations to incorrect values or passing null pointers to required parameters are generally not explicitly handled and will simply result in crashes or undefined behavior. Oh, so that's why we weren't getting any problems. Well, no, because... Okay. So what's the point of this, then? Oh, also, this has no inline documentation. So the Vulkan API has the same problem as the OpenGL API. Vulkan documentation. If I could do this in like a man page, that'd be nice. VK create instance. Oh, that was really slow. But hey, at least I don't have to use glad. So that it is still better. Okay. Because Vulkan requires you to be very explicit in everything you're doing, it's easy to make many small mistakes, like using a new GPU feature and forgetting to request it at logical device creation time. However, that doesn't mean that these checks can't be added to the API. Vulkan introduces an elegant system for this known as validation layers. Validation layers are optional components that hook into Vulkan function calls to apply additional operations. Common operations of validations are checking the values of parameters against the specification, tracking creation and destruction of objects to find resource leaks, checking thread safety by tracking the threads that calls originate from. Okay, that's actually really nice. Logging every call and its parameters to the standard output. Tracing Vulkan calls for profiling and replaying. This PDF with 5,729 pages of spec. That is crazy. The thing about extensions is that none of the implementation is actually required to collect activated extensions. You can just skip this step and use extensions anyway. But checking extensions lets you log and choose a different execution path. Okay, I see. Thank you. So I don't need to panic in this case. It might just, whatever. Okay. Here's an example of what the implementation of a function in a diagnosis validation layer could look like. Okay. I see. So basically, the default behavior of Vulkan is like OpenGL, where it'll just heckin' go on and things will just break. But if you want to install validation layers, you can, and then it'll make use of VK result in good ways. Okay. So yeah, this VK call that we made that just panics whenever anything goes wrong is probably a bad thing to do in a real program, but it's really going to be really useful for debugging. So we actually could, like, if def debug, then we define this. and then else define vk call func name, and then just do func name va args, and then it doesn't even check the result. Something like that. Validation layers are a must for Vulkan. You'll depend on them. Yeah. Yeah, we're going to keep this for now, but we'll see. These validation layers can be freely stacked to include all the debugging functionality that you're interested in. So, like, on the one hand, you probably don't want the validation layers to exist in the production builds, but it would also be useful if someone's having a weird graphics problem. You could go into the like hidden other settings and enable all the Vulkan validation layers, and then they can give you all the information that it spits out, which would be really useful for debugging. So it's probably useful to include a toggle for validation layers in the game. Like a theoretical Vulkan implementation of Factorio could do that. Okay. Linergy Vulkan SDK provides a nice set of layers that check for common errors. They're also completely open source, so you can check which kind of mistakes they check for and contribute. Using the validation layers is the best way to avoid your application breaking on different drivers by accidentally relying on undefined behavior. Validation layers can only be used if they have been installed onto your system. I'm pretty sure I already have them. For example, Linergy validation layers are only available on PCs with the Vulkan SDK. There were formerly two different types of validation layers. Okay, formerly, so we don't need to read any of that. Okay, let's just move on. Using validation layers. In this section, we'll see how to enable standard diagnostic layers provided with Vulkan SDK. Just like extensions, validation layers need to be enabled by specifying their name. All the useful standard validation is bundled into a layer included in the SDK that's known as VK layer Chronos validation. Okay. Yes, I do. I do have the validation layers installed. Okay, cool. Let's add two configuration variables to the program to specify layers to enable and whether to enable them or not. I've chosen to base that value on whether the program is being compiled to debug mode. The ndebug macro is part of the C++ standard. It means not debug. I don't think that's in C though. If, def, and debug. No, it's not. So we're gonna need to create our own Meson. I don't actually know how to do this in Meson. I could just do cargs. And then we'll just hard code it to debug for now, and then we can comment that out whenever we want to change it. But I need to figure out in Meson, because Meson has Meson configure build type equals release. And then it even shows you like all the things. Build type release, you can do plain debug, debug optimized release, min size, or custom. So I need to figure out how to branch on the build type in the Meson big file. Ah, that's easy. Okay, so I don't even need to do cargs up here, right? 13 EOL got colon. Oh, you don't need a colon. It's not Python. Yep, there we go. That seems to have worked. Okay. So now if we go in here, we should have an if def debug. Or not. Oh, wait, I said it to release, didn't I? Try keyword or argument language. Ah, there we go. Now it's working. That's pretty nice. Awesome. Depends highly what I want to happen. The build type option is meant to describe the current build's intent. That is what it'll be used for. Individual options are for determining the exact state is. This becomes clearer with a few examples. Suppose you have a source file that is known to miscompile when using O3 and requires a workaround, then you write something like this. On the other hand, if your project has extra logging and sanity checks that you would like to be enabled during the day-to-day development work, you do this instead. Okay. But I think I want this to be, instead of equals debug, I want it to be not equal release. Or no, we'll just do debug. Yeah, that should be fine. Yep, it's still working. Awesome. Cool. Mizan is pretty cool. All right. So now we can do... I probably will want to start splitting these into separate files at some point. This is kind of getting messy. But let's at least put all of our constants at the top, then all of our variables, then all of our functions. So this will be... Oh, frick, that's a vector. We can't statically allocate a vector. No, yeah, we can. Well, we can statically allocate a pointer. Are autoconf and ninja interchangeable? I do know you can change the backend that Mizan uses. You can use CMake if you want. Or you can use make. You can make Mizan generate make files and then use make, but why would you do that when you can just use Ninja instead? Okay. Okay, so that's const. Oh no, that's constant vector. Okay, so we can do const car validation layers. Well, we can make this a statically allocated array. Oh, KHR stands for Chronos. Aha! I figured it out. All right, so that's a const car there. These are constants, so let's put those above the global state. Okay, cool. Okay, without a new function, check validation layer support that checks if all the requested layers are available. First, list all the available layers using VK enumerate instance layer properties. Yeah, okay, so you need to do the count and then do the that. Do the that, okay. Okay, so do I order these functions in the same order that they're called? Yes. Or reverse order, because I could have put this up here. I guess if it's going to be called in the initialization, then it would need to be up there. Oh, yeah. Yeah, it does need to be used in there, so we need to put it up here. Okay, so we get layer count. Okay, VK enumerate instance layer properties. Layer count. And then after we get that, we allocate our... Oh wait, did we end up freeing this? Are we leaking memory already? Hold on. I think we're already leaking memory. Yes. Classic C programming. Always have ASAN turned on. Okay, we are leaking because we're destroying the properties, but we're C allocating this available extensions and then we're not freeing it. So we need to free available extensions. See if that helps. What even is all this? That's a lot. How are we possibly leaking this much already? What's going on? SDL will leak to at exit. But I'm cleaning it up.
Fix it, fix it, fix it, fix it, fix it, fix it.
Destroy surface.
Fix it.
Create surface. Unload library. See if that works. No. Jeez. This is all X11 garbage. Get global content scale, X11, and a lot of these. Okay, let's try running it on Wayland and see if that helps. Yes. Okay, so all of the leaks are in the X11 implementation. Well, SDL leaking memory is bad for me because it adds noise to ASAN. So I would need to find a way to make ASAN ignore any memory allocated by SDL. But that's also kind of bad. But also switching it to Wayland fixed it, so yeah, we're good. Woo! Okay, so we're no longer leaking. If I remove this free, then it should tell us that we're actually leaking that. Yes. And that is actually useful. But now we're no longer leaking. Awesome. Cool. Okay, check validation layer support. That's what we're working on. Okay, so we enumerate that. And then the reason I thought of that is because now we need to const VK layer properties pointer available layers equals C outlook. Maybe I ought to write a macro for this as well. Like define array, make array, something like this. Type name and size. It's probably not worth a macro for this. This is, yeah, no, we're not gonna do that. That's dumb. Okay, and then we basically copy paste this, but instead we pass available layers. Yeah, we're good. Maybe we ought to do something like this, but no, that would only work if the arguments are in the same order. Make begin to end macros. No, let's do this. Define true, false. Define false, true. Ha! Oh no, but that's recursive. No! Because that's just defining true, true. Heck. Okay, Next, check if all the layers and validation layers exist in the available layers list. Now we're just going to copy this. Except we can't. Okay. For const car layer name, so for uint 32. How do I get size? How do I iterate an array? Because I know the size. I guess I'll just have to define it. There we go. Size of array divided by size of element. Yeah, that would actually work. Javero, you can see the current song in the bottom right. I have not set up stream elements stuff yet. Right, because we're not... Yeah, this size of the validation layer should be... No, that is size of pointer. Oh no, it is array. No, you're right. Huh. Because otherwise this would be const car pointer pointer. Right. Okay, we're good. All right, so that should work. So for every validation layer we want, so I want a layer name, an available layer name. I see. Yeah, that works. Okay, we can now use this function in create instance. If enable validation layers, so we do this like immediately. If enable validation layers and not check validation layers support. Panic. Validation layers requested, not available. All right, cool. Oh, we're also leaking this. This is where I'd really love a defer keyword. Like, C would be so much better if we had to defer, because then you could just defer free available layers. Like, that's... I might use C++ just so I can make a scoped callback. We have this in Factorio, where we have a scoped callback function, which or scoped callback thing, which basically just runs the lambda when it's freed or when it goes out of scope, and it's super nice. Because now I have to do here. So like if I'm a real boy C programmer, I would use a goto here. Goto failed. Then failed. Free available layers. Turn false. Like that. That's awful. Make a C+, it's pretty much C, but with defer keyword. You don't need zig bindings for C? Yeah, I actually, if I was gonna use anything, it would be C3. C3 does have defer. Pretty sure. Yeah. C3 does have defer, and it has namespacing, which is pretty much like all I want. C would be great if I had defer and namespacing, but it also has some other things, like it has actual vectors. So not an array list, actual vectors with swizzling and dot products and stuff as a first-class citizen. It's so cool. Zig is a C compiler anyways. True. I've been meaning to try Zig, but it's just been on my list. I think I like C3 better though, because it does less over C. Like it keeps a lot of the C-isms, like it doesn't make you pass allocators to everything, like Zig does. But yeah, I just love these vector types. They're so fun. Like vectors as a first-class citizen makes so much sense. And then it also has generics. You can have generic modules. So it has a module system, but then you can make a generic module that you can then import for certain types. So then you can alias foo float is a foo module with the types float double. And that's a really nice way to do generics because it keeps it simple, but also keeps it really useful. Then it has these weird contracts. I don't understand why these are so hyped. Just make asserts in your code. Like, how is this different from asserts? Like, you're making the parser more complicated, and you're making comments have meaning, which I don't like. But it's like all the hype nowadays for some reason. Now run the program in debug mode, ensure that the error does not occur. If it doesn't, have a look at the FAQ. Okay. So let's just make our own validation layer and see if it fails. Yes. Okay, so let's assert, defer, assert, done. Yeah, exactly. Like I don't understand why it needs to be in contracts. Well, actually these are more like it's like meta programming, sort of. Like you're requiring that one can be assigned to type B, or that type B and type C are assignable. But like at that point, just do runtime reflection. Like it already has runtime reflection, so just do assert my type dot is assignable. Like, I don't get why you need contracts and comments. I don't like that at all. But other than that, I really like C3. I should have done this in C3. Okay. Finally, modify the VK instance create info struct instantiation to include the validation layer names if they are enabled. If enable validation layers, create info.enabled layer count. Sorry, instance. I'm gonna rename this. Instance create info. Instance create info dot enabled layer count equals yeah. We're gonna validation layers count. Validation layers count. Instance create info dot enabled layers. PP enabled layer names equals validation layers. Go. And we don't need to initialize that to 0 because unlike C++, C has structured initializers or initializer lists that will automatically initialize everything else to 0. And it is so nice. Why doesn't C++ have this? It's like what this lets you do, like in C++, if C++ had this, then you could just do like myfunc, call it with an anonymous constructor, and then put ASDF equals true. Then everything else would be null. But no, I've tried this in C++, Barracuda. How do you do it? Like, C++ makes you initialize them in order, and it makes you initialize all of them, in my experience. Maybe that's some compiler flag that we have or something. I don't know. But I've never been able to do that in C++. Godbolt it? Thank you. I would appreciate that. The resident C++ expert in the chat. If the check was successful in the VK create instance, should not ever return VK layer not present, but you should run the program to make sure. Seems error prone to have implicit defaults. Maybe. But I think it's worth it. Okay, why does Clang format do that? There's no reason, there's no situation in which that is the desired behavior. Always put it on the next line, thank you. C++ says one requires you to define them in declaration order. Yeah, that's why I hate it. Because like in C, I can just put that up there, put that down there, and everything's fine. But in C++, it makes you do it in declaration order. Layer count 2, thank you. Okay, cool. All right, message callback. The validation layers will print debug messages to the standard output by default, but we can also handle them ourselves by providing an explicit callback in our program. This will also allow you to decide which kind of messages you would like to see, because not all are necessarily fatal errors. If you don't want to do that right now, then you may skip this to the last section in this chapter. I think I will do that later, because I kind of like having them just jump to stood out. So that's fine. So we will do that later. Yeah, because that's a lot. We might come back to that. Okay, debugging instance creation and destruction. Although we've now added debugging and validation layers, we're not covering everything quite yet. The VK create debug utils messenger ext call requires a valid instance to have been created, and VK destroy debug utils messenger ext. Is that from here? Yeah. Oh, it wasn't. Okay, so if we don't destroy the instance, then it should tell us. It didn't. Neat. It's not even giving us an ASAN error either. I'm surprised that not leaking. We do still have ASAN enabled, right? Yes. Right, but they said that the default behavior is printing to stood out, so like it should print stuff now, but it wasn't. Maybe it's fine. We actually are gonna comment out this main loop because it's not doing anything useful right now. Okay. If you don't want to do that right now, you may skip to the last section in this chapter, which is configuration. There's a lot more settings for the behavior validation layers than just the flag specified in that. Browse to the Vulkan SDK and go to the config directory. There you'll find a vk layer settings.txt file. There, it doesn't exist. Cool. Oh, there's a Chronos Vulkan tutorial. Oh, wait, this is the same tutorial that we're doing over here. But this one... This one's more up to date. It's also way laggier. Jeez. Like, wow, that's way laggier. DK guide. Oh, this is like completely different. Initializing Vulkan. Yeah, this is giving me a lot of code. I don't know, this is completely different. We're gonna keep going with the Chronos guide, I think. But we are going to do it on this website because even though it's slower, like significantly slower, it was telling us about the C++ library, which means it might be more up to date. Thought this was going to be a stream about Vulcanist? Nope. No Factorio today. After initializing the Vulkan library through VK instance, we need to look for and select a graphics card in the system that supports the features we need. In fact, we can select any number of graphics cards and use them simultaneously. But in this tutorial, we'll stick to the first graphics card that suits our needs. That's crazy. Okay, let's look at the God Bolt that you brought up. Huh. Wow, look at all these includes. What happens if I remove that one? C++ 26, really? Also, that is heckin' slow. You don't clean includes? Okay, that's fine. I should only really need the print. Yeah, okay. Huh. So it does let you be optional, but it also makes you do it in order. Wait, what? That worked? Oh no, it's a warning. Okay. But it's not an error. But we have W error turned on in Factorio, so like we have no warnings. If there are any warnings, they're errors. Because that's how you should be doing it. If you have a bogus warning, then you disable that warning. But you don't let yourself ship code with warnings. Okay, so you can do it, but it just yells at you. Okay, that's interesting. Well, thank you. Okay. So we need to pick a physical device. So let's pick physical device. Okay. Graphics card that we'll end up selecting will be. Oh, this is using. Oh, this is using the C++ API. Okay, so that's the difference. This uses the C API, but this one uses the C++ API, which is what I was going to do originally. Then I decided to do it in C because C++ makes me angry. Okay, so yeah, so we will continue with this one then. Okay, we're probably gonna need this to be. What is that? That's just null. Get out of here. The other one is also C++, is it not? Yeah, but uh, this one is using C++, but it's using the C API of Vulkan. Whereas this one is using the C++ API of Vulkan. Like this one is having us use VK RAII physical device, whereas this one is using VK physical device. Experimental scope. Oh. Scope is normally exit. Okay, that's cool. But then scope exit. Huh. Cool. But we already have a built-in type for that, so like, or we already have our own type in Factorio, I mean. Basically, unique resources, unique pointer for handlers, and scope exit, scope fail, scope success are very old concept that finally got into standard. Nice. Yeah, having defer as an actual keyword in the language would be awesome though. Okay. Yeah, okay, so it's the same kind of thing. There's a lot of boilerplate, but that's fine. Because now we're using our VK instance. And then we do our same song and dance const VK physical device devices. You can enumerate physical devices. Wait, I'm an idiot. Simple drop, yeah. Okay. So now we evaluate each of these to see if they're suitable devices. This is just a Okay, we are going to start wrapping all these in VK calls. Kind of the whole point. Okay, cool. So return true. All right, cool. All right, cool. Next section will introduce the first requirement that we'll check for in is device suitable function. As we'll start using more Vulkan features in the later chapters, we'll also extend this function to include more checks. Okay. Yes, I know it's a C23 extension. I'm using C23. Stop warning me about that. It literally doesn't matter that this is. It's also not going to complain if I actually compile it. It's just a Clang D thing. Yes, I know it's a C23 extension. I'm using C23, so stop. There, you happy now? Okay. I am going to take a short break. I'll be back later. A few minutes. I'll be back. I have returned. Hello, pseudo render me a sandwich. We are making a triangle, hopefully. I know we've written 182 lines of code and we still don't have a triangle, whereas with STL GPU, we had a triangle with 208 lines of code. So, yeah, this is our goal, but with Vulkan instead of STL GPU. Okay. I don't think we need STL anymore. We haven't used it. Okay. Basic device suitability checks. To evaluate the suitability of a device, we can start by querying for some details. Basic device properties like the name, type, and supported Vulkan versions can be queried with vk get physical device properties. Okay. Oh, that doesn't return a vk result. Interesting. Vulkanist was too easy, so now we do Vulkan. Exactly. What window manager to use? Sway. Basically i3, but Wayland. And Crackalakin. Hello. Narek, change the way you write an exception-safe code. Implementing scope guard. Ah, yeah. I will add that to my reading list. Okay, so we enumerate the device properties. Let's actually look at what our device properties are. Here we are. API version 1.4.305. Okay, so we have a few things here. It's a discrete GPU. It doesn't have limits. Oh, yes, it does. It's down there. Max image dimension 2D. Oh, really? Max image dimension 3D. You can only have a 248 but 248 image and 3D. What? Okay. What does that mean? Or for optional features like texture compression, 64-bit floats, and multi-viewport rendering can be queried using physical device features. Okay. Oh, 2048 cubed. Okay. Why is it so hard to make a triangle? Because Vulkan. I have heard rumblings that Kronos wants to rewrite OpenGL as a layer on top of Vulkan, which would be pretty freaking based. Then it'd basically be Vulkan easy mode, and then you can opt into Vulkan features or whatever. I don't know. That'd be cool. Okay. There are more details that can be queried from devices that we'll discuss later concerning device memory and queue families. Right. I actually had to do this in Factorio. 1 second. I'm going to show you something. So here's a little fun fact for you. Factorio does use Vulkan. For one specific thing. Hold on. Pay no attention to the man behind the curtain. There we go. Yeah, Factorio does use Vulkan. It uses Vulkan to get the dedicated video memory size. And I actually added this bit of code in like a couple weeks ago because our detection of VRAM on the Steam Deck was not working correctly. So it was saying the Steam Deck only had like 512 megabytes of VRAM instead of 8 gigabytes. So yeah, I had to add this little bit. Yeah, we use Vulkan to get the dedicated video memory size. So we have, here's our scoped callback. That's our defer. But we create an instance of Vulkan 1.0. We enumerate instance layer properties. Create instance. We enumerate physical devices. Yeah, so I am already familiar with this. It's pretty neat. Okay. Because Vulkan has a much more accurate view of the Steam Deck's VRAM than OpenCL did. Okay. As an example, let's say we consider our application only usable for dedicated graphics cards that support geometry shaders. Then the isDeviceSuitable function would look like this. Device features. Robust buffer access, full draw, index uint32, image cube array, independent blend, geometry shader, tessellation shader. Wow, there's a whole lot. But it probably does not support AV1. Yeah. Right, my GPU does support AV1 decode, but not AV1 encode, which kind of freaking blows. Because once Twitch supports AV1 encoding and enhanced streaming or whatever it's called, I'll have to get a new GPU. Forgot to mention there are two ways to render in Vulkan: render pass and render pass less. The tutorial will teach you the legacy way. Interesting. Well, when we get there, I will do the tutorials way, and then we'll try implementing render pass less using the documentation, and then we'll see which one I like more. Except for streaming, you'd want to encode AV1 on the CPU anyways. Well, the whole point is you have enhanced broadcasting, I think is what it's called, where instead of forcing Twitch to transcode your video, you do it yourself. So you encode like all of the different resolutions at the same time so that Twitch doesn't have to. And that solves all the problems with like being able to not being able to go above 14 or not being able to go above 1080p in certain countries. So I would want to do that with AV1 so that I could have the AV1 encoding for the best visual quality because AMD's H.264 encoder is not very good. And then I would simultaneously stream all of the different sizes because I have enough bandwidth for that. Yeah, you would definitely want to do that on the GPU. Okay. As an example, yeah, okay. Instead of just checking if a device is suitable or not and going with the first one, you could also give each device a score and pick the highest one. That way, you could favor a dedicated graphics card by giving it a higher score, but fall back to an integrated GPU if that's the only available one. You could implement something like that as follows. Okay, so you'd pick physical device. What's a multi-map? Never seen that before. Multi-map is an associative container that contains a sorted list of key value pairs. Okay, so it's sorted. While permitting multiple entries with the same key. Huh. Yeah, the encoder is better on the new 9000 series GPUs, but I already spent $3,000 on tech this year, so I need to wait till next year before I can let myself upgrade my PC. Still rocking my 10900K and 6800 XT, and they're still plenty good for everything except streaming. Yeah, that's cool. Anyway, so they use a multi-map. Oh, okay. So they use a multi-map so that it automatically sorts by increasing score. Huh. That's weird. I think in C, I would just make an array of all the physical devices and then make a like a struct. So we would do this like typed struct pk or physical device and score. Or we could just use properties and then iterate them and return the highest one. That's probably the easiest way. But I was gonna say we would make a struct with the physical device and score. It'd have a vk physical device, and an int score. And then you would just do qsort on that. But if we use properties, then we would still need a callback function. That's annoying. I want lambdas. Okay. Yeah, they use that, and then they rate device suitability, and then they insert it, the score and device. Yeah. So then it automatically sorts it, and then they take the highest one and use that. Okay. So discrete GPUs are preferred, and then the max image dimension 2D. Yeah. Okay. No anonymous functions in C? Nope. Not that I know of, anyway. So yeah, we could implement all this, but we'd have to figure out how to do it in C, and I don't really feel like it. So we're just not gonna. Okay. Queue families. It has been briefly touched upon before that almost every operation in Vulkan, anything from drawing to uploading textures, requires commands to be submitted to a queue. There are hold on. Need hydration. There are different types of queues that originate from different queue families, and each family of queues allows only a subset of commands. For example, there could be a queue family that only allows processing of compute commands, or one that only allows memory transfer related commands. Okay, so that's like creating a transfer buffer and stuff. We need to check which queue families are supported by the device and which one of these supports the commands that we want to use. For that purpose, we'll add a new function, find queue families, that looks for all the queue families we need. Okay. Okay. However, in one of the next chapters, we're already going to look for yet another queue, so it's better to prepare for that and bundle the indices into a struct. Oh, well, it fooled me. Okay. Okay. Awesome. What if a queue family is not available? We could throw an exception, but this function is not really the right place to make decisions about device suitability. For example, we may prefer devices with a dedicated transfer queue family, but not require it. Therefore, we need some way of indicating whether a particular queue family was found. It's not really possible to use a magic value to indicate the non-existence of a queue family, since any value of UN32 could in theory be a valid queue family index, including 0. Luckily, we have stood optional. Okay. How about we do a little sneaky There, that's it. If there are 4 billion Q families, then we will have a crash or a bug. But other than that, we're fine. Are you enjoying GPU land yet, where everything has a billion different standards and supports different things? Oh, I haven't really gotten far enough to really for that to be a problem. So. Yeah, we use this trick in Factorio a lot where we don't want to wrap something in a std optional because that makes it larger and it makes it slower to compile. So we will often use the max value of something to mean invalid. Nice. You can store Q indices as UN64 and the negative one will never be filled. You know, that's true. We'll consider that. Okay. But it might be annoying because then we'd have to cast this to UN32 every time we want to use it. So I don't really want to do that. But we'll see if that ends up being a problem. Okay, we can now begin to actually implement find Q families. Process of retrieving the list. Yep, it's exactly what you would expect. Okay. And because C++ has no niche optimizations, it's a pretty neat part in Rust. What do you mean by niche operations? Like it'll optimize out the tagged union if it can statically asserts that it'll always be true, or like what? What do you mean by that? Oh, speaking of freeing. Okay, cool. Okay, so contains some detail about the Q family. So let's okay, Q properties. Okay. Video properties, KHR. Yeah, niche optimization is that I can use the value from some T variant that is not used. So option non-zero U8 would still just be 1 byte since it can reuse 0 to indicate none. Oh, interesting. That is cool. Okay. So for each Q family, it would help if I could type. Cool. Now that we have this fancy Q family lookup function, we can use it as a check in the isDeviceSuitable function to ensure that the device can process the commands we want to use. Oh, indices is complete. Okay, how is that implemented? Ah, a graphics family that has value. There we go. Yeah, I'll just leave it like that. That's fine. It's used one time. Great. That's all we need to now find the right physical device. Okay, so now we should be finding a physical device. Cool. Pick physical device. Printf. Yep. Cool. Okay, actually, we want to probably printf physical device dot name. Oh, they must be in the properties. Yeah, you're probably right. There we go. So it is picking the 6800 XT. Okay, I will be back in 2 seconds. I need to refill my water. Okay. Hydration has been refilled. Vulkan, hardly newer. That does not work. No. Be like Volker, hardly newer. It has to end with preferably her. Okay. Right. Okay. So now we've found the physical device. I think I kind of want to actually go back and do that validation layer thing, like all the logging garbage maybe, because well, no, we'll do that later. I was gonna say I want to start hooking some stuff into SDL's logging infrastructure, but we probably don't need to do that yet. Because I wanted to do like SDL log info. But then I would put this in like an SDL log trace. Want to enable debug layer as soon as possible, otherwise you'll drown in mysterious crashes. Yeah, I mean, I'm already doing that. I'm already doing the validation layers. It's just I'm not having a custom validation layer print hook. Isn't Doom made on Vulkan? Yes. You have to see implementation that does not have graphics, compute, and transfer bits in first queue family. Spec declares that one family must have both graphics and compute operations. And additionally states that transfer must be supported if any graphics or compute operations are supported. So it's quite safe to pick first and be it. Yeah. But I'm just following the tutorial, man. Okay, so you have a physical device, but then you need to create a logical device that abstracts over the physical device. Do I have to free this? No, it's stack allocated. Oh, and this doesn't support... Oh. I guess it does. Yeah, there we go. I was going to say that doesn't support printf, but it totally does. By default, the application and GPU categories are enabled at the info. Yeah, let's do GPU. The only downside to this is it kind of intermingles with SDL's log categories. So I might want to do my own. There's a reason for learning Vulkan in the aspect of new technology hobby project, or is Wuba wanting Vulkan? A little bit of all of those. I would like to know Vulkan so that I can contribute to graphics stuff at my work, but I'm not gonna confirm or deny the existence of any Vulkan branch on Factorio. Like, no, I'll just deny it because there isn't one. There is no Vulkan work being done in Factorio at this exact moment. No, I did deny it. I've changed my mind. So why aren't you logging? All our categories are enabled at the error level. Oh. Vulkan even have a benefit in Factorio? Probably not, to be honest. Factorio works well enough on OpenGL that like we don't really need to do Vulkan. That's why it's never happened. If there was an actual benefit to putting Factorio on Vulkan, like a tangible one, then it probably would have happened by now. But hey, I mean, StrangePan ported it to Metal, and that actually had pretty good benefits, so maybe, but we'll see. I will reveal some information that I don't think is public. There was a Vulkan branch at one point during the 1.1 development cycle, but it was abandoned and never finished. It worked on Linux, but it didn't work on anything else, as far as I'm aware. Does Vulkan require SDL? No, you can use any windowing, or you can do it. You can just raw dog Wayland if you want, and it'll work fine. Okay, but this isn't logging nothing. Whatever. Too much work. It's overkill for a project this small. There we go. Initialize Vulkan on the AMD Radeon RX 6800 XT. Cool. Okay. After selecting a physical device to use, we need to set up a logical device to interact with it. The logical device creation process is similar to the instance creation process and describes the features we want to use. We also need to specify which queues to create now that we've queried which queue families are available. You can even create multiple logical devices from the same physical device if you have varying requirements. Gotcha. Start by adding a new class member, store logical device handle in, okay. VK device equals null. Okay, and then in our init, we need to physical device create logical. Okay. Let's find the queues to be created. The creation of a logical device involves specifying a bunch of details and structs again, of which the first one will be VK device queue create info. Okay. The queue priority is queue count, queue family index. Okay. Structure describes the number of queues we want for a single queue family. Right now, we're only interested in a queue with graphics capabilities. That's guaranteed to exist at this point. Haven't touched SDL since 2003? Wow. SDL's come a long way. SDL was old. Ugh. Okay. You create info S type. Oh yeah, I need to do this. The queue family index is index.graphics family. Queue counting is 1. Okay, what does queue priorities do? Okay, I need to figure out how to actually Vulkan documentation, Vulkan specification, Vulkan guide. Why is this website so slow? Okay, VK device, queue, create info. Can I just get reference documentation, please? There's an offline version of the Vulkan API, probably. Vulkan API offline docs. Download docs link at the top of the docs navigation panel. False. vkspec.html. Aha. And it's also slow as hell. That's fine. Okay, there's no Vulkan docs package. Man, Vulkan? No. Would have been too good. Oh, geez. It's just completely frozen. Come on. Come on. Come on, I'm not like Vulkan is like high performance GPU API. Their website is low performance website. Jeez Louise. Holy. Why is Bitwarden slowing down Libre Wolf? A 5,000 page document. PDF, yes, thank you. $6,000 pages. Oh gosh. Uh, Zathura is not happy. Aww. And that's Zathura. Oh, oh, frick, my RAM. Oh, jeez. Oh, gosh. My computer almost just ran out of RAM. That was scary. It went up to like 80%. It used like 40 gigabytes of RAM. Okay, well, how? Okay, VK device queue create info, please. Give me Chronos registry. Okay. How do I search the registry? I use page up, page down keys, no smooth scrolling. Okay. Queue priorities is a pointer to an array of queue count, normalized floating point values. There's got to be a way. Vulkan API man pages. Autogenerator Vulkan docs man pages 5 years ago. Okay, this actually looks closer to what I was trying to do. But it has a non-resizable sidebar that is not large enough. Okay, here we go. Queue priorities is a pointer to an array of queue count, normalized floating point values. Specifying priorities of work that will be submitted to each creative queue. See queue priority for information. Okay, so we don't need to worry about that. Vulkan docs readme OV file. Vulkan device specification and related tools. Wait. Is that just ASCII docs? I just wish that my distribution had a package to install this. Okay, well, I'll figure this out off stream. Make, clean, install. But we're just gonna follow the tutorial. Okay, so we just do that. Queue create info. Okay, currently available drivers will only allow you to create a small number of queues for each queue family. You don't really need more than one. That's because you can create all the command buffers on multiple threads and then submit them all at once to the main thread as a single low overhead call. Vulkan lets you assign priorities to queues. Oh, hey, here it is. Vulkan lets you assign priorities to queues to influence the scheduling of command buffer execution using floating point numbers between 0 and 1. This is required even if there's only a single queue. Wait. Huh? Okay, so what happens if we don't do that? We're gonna try that later. Okay, so we're gonna comment that out and see what happens. Okay. Next information to specify a set of device features we'll be using. Oh, jeez. Woo! Okay. These are the features that we create support for with VK get physical device features. I don't remember doing this. Why? How have I already forgotten? Oh, I deleted it. It was in pick suitable device. Is device suitable? That's why I don't remember it, because I deleted it. Went in one ear, out the other. Okay. Right now, we don't need anything special, so we can simply define it and leave everything to VK false. Okay, so that's all we need. Creating a logical device. Cool. VK device, create info. Create info. Okay, Q create infos equals Q create info. Q create info count is 1. I actually got that without even looking at the tutorial. P enabled features equals device features. Okay, and then we VK call, VK create logical. VK create log. Oh. Remainder of this information bears a resemblance to VK instance create info struct and requires you to specify extensions validation layers. Reference that these are device specific this time. An example of a device specific extension is VK KHR swap chain, which allows you to present rendered images from that device to Windows. It is possible that there are Vulkan devices in the system that lack this ability, for example, because they only support compute operations. We'll come back to this extension in the swap chain chapter. Okay. S-type, thank you. Yep, I overlooked it. I keep forgetting these are C tagged unions, and they are, yeah. Oh, it's just VK create device, of course. A physical device, and then create info, then allocator, and then device. Cool, and that does return a VK result, so yeah, we're good. Okay, previous implementations of Vulkan made a distinction between instances and device-specific validation layers, but that's no longer the case. That means that enabled layers count and PP enabled layer names fields are ignored. However, it's still a good idea to set them anyway. Okay, whatever. Vote for Vulcanist got more work after work. Nice. Hello. Only need device-specific extensions for now. That's it. Cool. Now we can create the device. Parameters, run. Ah, okay. Validation error. Okay, so the validation is working fine. PQ priorities is null. That's what I was testing. Okay, now we have a zillion leaks because we're not freeing any of these things. VK destroy device. Device null. VK destroy physical device. Oh, just see if that fixes it. Yes, okay. Oh, hey, and there it is. Nice. Parameters are the physical device, the queue, and the usage info, and the optional allocation callbacks. Similarly to the instance creation function, this call can return errors based on enabling non-existent extensions or specifying the desired usage of unsupported features. Looks like you might be able to blame Vulkan for the lack of documentation. It's probably not in distro Vulkan packages because it's in a different repo to the actual code, yeah. The destroy physical device, GPU explodes. True. Okay. Logical devices don't interact directly with instances. That's why it's not included as a parameter. Interesting. But you have to use an instance to query the enumerate physical devices. Yeah, so you do need to create the instance first. Retrieving queue handles. The queues are automatically created along with a logical device, but we don't have a handle to interface with them yet. First, add a class member to store the handle to the graphics queue. Okay. Device queues are implicitly cleaned up when the device is destroyed, so we don't need to do anything in cleanup. We can use the VK get device queue function to retrieve queue handles for each queue family. Okay, create logical device. So we do that here. And then, okay, call device queue. Oh, it's void. Okay, so that can't error? Okay. What does it mean I can blow up potentially GPU? Okay, cool. So now we should have a logical device. With the logical device and queue handles, we can now actually start using the graphics card to do things. In the next few chapters, we'll set up resources to prevent results to the Windows system. Cool. We have finished setup. 3 hours and 30 minutes in, and we've finished the setup. Now we can get to presentation. I would unplug my GPU just to see what happens, but that would kill the stream, so. Okay, since Vulkan is a platform-agnostic API, it cannot interface directly with the Windows system on its own. To establish a connection between Vulkan and the Windows system to present results to the screen, we need to use the Windows System Integration extensions. In this chapter, we'll discuss the first one, which is VK-KHR Surface. It exposes a VK Surface KHR object that represents an abstract type of surface to represent rendered images to. The surface in our program will be backed by the window that we've already opened with STL. VK-KHR Surface extension is an instance level extension. We've already enabled it because it's included in the list returned by those. I'm going to print the STL extensions. Okay, so it just needs VKKHR display and VKKHR device group creation. Huh, that's not very many. Wait, so it doesn't need a VKKHR surface? Right, so we're using SDL, so this doesn't need surface. Huh. That seems sus. Surely it needs surface, right? SDL extension count, yeah. Oh, wait. Ah, there we go. There we go. That makes a lot more sense. VKKHR surface, VKKHR Wayland surface. Okay. There we go. And I assume if we remove the Wayland call, then it will require SDL X11 is awful. Wow. But it didn't even print it. Nice. Yeah, there it goes. Enable extensions required. Yeah, xlib surface. Okay. But we're gonna go on Wayland because SDL on X11 leaks like crazy. So. Okay, but now we've confirmed that SDL requires KHR surface. Cool. SDL is just happy to run on X11. It's true. Okay. Anyway, the Windows surface needs to be created right after the instance creation because it can actually influence the physical device selection. Interesting. The reason we postponed this is because Windows surfaces are part of the larger topic of render targets and presentation, for which the explanation would clutter the basic setup. It should also be noted that Windows surfaces are an entirely optional component in Vulkan if you just need off-screen rendering. That's actually cool. Vulkan allows you to do that without hacks like creating an invisible window. Okay, so now we need VK surface KHR. Actually, we're gonna add this. Can I like include the subprojects folder itself? That's fine. Okay, so that's the setup chapter. Cool. Okay, so we VK surface KHR surface. Although the VK surface KHR object and its usage is platform agnostic, its creation is not because it depends on Windows system details. For example, it needs hardware. It's the I keep saying hardware and in my in my head, but it's handle window and handle module handles on Windows. Therefore, there is a platform-specific addition to the extension, which on Windows is called VKKHR 132 Surface. Okay, but we are using Wayland Surface. Won't actually use it in this tutorial. It doesn't make any sense to use a library at GLFW and then proceed to use platform-specific code anyway. Yeah, okay, so we're going to ignore all of that. Okay, so let's just go down to our initialization here. Init Vulkan, SDL Vulkan create surface. So we need our window and our instance. Construct VK allocation callbacks allocator null surface. Easy. Great surface, baby. Okay, but it told us that it's VK destroy surface. KHR. Instance surface. Cool. Easy. Fine, I guess I'll do it here. Create surface. Gosh, I'm getting hungry. But I don't want to stop streaming. So I might take a break and then cook some dinner and then come back. There we go. Okay, so it literally just does that. That's funny. But hey, it's working. Cool. Okay, querying for presentation support. Start screaming instead. Although the Vulkan implementation may support Windows systems, that does not mean that every device in the system supports it. Therefore, we need to extend isDeviceSuitable to ensure that a device can present images to the surface we created. Since the presentation is a queue-specific feature, the problem is actually about finding a queue family that supports presenting to the surface we created. It's actually possible that the queue families support drawing commands, and ones supporting presentation do not overlap. Therefore, we have to take into account there could be a distinct presentation queue by modifying queue family indices. Okay. We have to create a separate present family. Ah, okay. Function to check for that is VK get physical device surface support KHR. Wait, but we call this before we create the surface. Well, let's just do it and see what happens. Also, that's a VK bool 32. Oh, why? Just use bool. Crap, annoying. Excuse me. Okay. Why? That's annoying. Yeah, that's what I thought. You need to have a surface. So why are we doing it here? Am I missing something? You just put window first, then instance, then surface. What? Oh, I see. So Vulkan complained about the null handle, and then it segfaulted. Physical device with Q families. It feels stupid. I don't understand what you're saying. You just put window first, then instance, then surface, then physical device with Q families. Oh, right. It was saying we need to do this like immediately. There we go. Right, because it was saying, yeah, okay. There it goes. Okay, that's the answer. So yeah, we create surface first after the instance so that by the time we pick physical device, yeah, okay. Yeah, that makes sense. Thank you. I completely missed that. Okay, creating the presentation queue. Okay, so now we need to create. Okay. Oh, this is using a set. Okay, next we need to have multiple VK device queue create info structs to create queues from both families. An elegant way to do that is to create a set of all unique queue families that are necessary for the required queues. I could use SDL properties and convert the queue family indices to strings and then convert them back to numbers, but that's horrible. Order and destroy also relevant? Oh, yeah. That was something that would have just been magically handled by RAII because it would have destroyed them in reverse order of how they were declared. Okay, so what is this doing? It's finding the indices again. That's annoying. It should just do it once and cache it, but that's fine. AK device can create info, set. My brain is shutting off, dude. Maybe I do need to go eat something. I kind of want to try to see if I can get through presentation today as well, and then I'll call today. Your priority, your family, unique key families. Right, so we're creating a queue for each unique Q family. Oh, and then here you do present family. VKQ is a handle for you to use over an index inside a Q family. Nothing more. You don't even need VKQ destroy. Yeah, that doesn't even exist. So we'll do that. But we need to create the Q families. Alright, so if these are the same, then it'll be fine. Oh, I see. So we're replacing this with the set. But that would be annoying. Okay, we're gonna do something really cursed here. Certainly there's an easier way to make a set in C, but we're just gonna do it this way. Oh, but then I have to enumerate this. Oh. No, we're not doing that. That's too cursed. Wait, hold on. I kind of destroyed what I actually needed. Why did I do that? Oh no, I didn't. It's still there. Yoink. Hey King, I'm doing okay. I'm really hungry though. Okay, so we're just gonna do that. Oh, this is where C++ would be real nice, actually. I'm gonna see if there's like a library for this. Tree-based approach, hash-based approach. I guess I could make a Oh, binary tree. Yeah, that makes sense. Sorry, I'm looking at how to implement sets. Yeah, actually using a binary tree sounds like huh. That is the way to do it. Yeah, that's correct. But I'm not implementing a binary tree. So what I'm just gonna do is I'm just gonna do this. There's an easier way, he says. So doing a simple if A equals B. Yeah. That's exactly what I started doing, Barracuda. I hate this, but it is the simplest way. There we go. Easy peasy. Okay, yeah, that's all we needed to do. Like, all we needed to do was add this, but I was overthinking it. There we go. All right. Blockchain. Okay, but seriously, I think I do need to take another break and go get some food. So I will be back in a minute. Well, a few minutes. Vulkan is just hipster GL. This mac and cheese that Costco sells is not very good. But it's food, and I have to finish it. I decided to try their mac and cheese that you would just cook in the oven, and I really don't like it. But I already made it, so I need to eat it. Okay. Honestly, I'm kind of tempted to just cut my losses and throw this away. I really don't like it. It was bearable when it was freshly cooked, but the reheated is not good. Okay, Vulkan does not have the concept of a default frame buffer, of course not. Hence it requires an infrastructure that will own the buffers we will render to before we visualize them on the screen. This infrastructure is known as the swap chain and must be created explicitly in Vulkan. Swap chain is essentially a queue of images that we are waiting to be presented to the screen. So I have a question about this. Like, Wayland is VSync by default, which means that it's already double buffered. So if you have a double buffered game, let's say we run some Factorio. If we have a double buffered VSync game like Factorio, Factorio is double buffering the frames that it sets to Wayland, and then Wayland is double buffering the results, so it's actually being triple buffered. Is that right? But then if I full screen it, it does direct scan out, so now the game is only double buffered. But if I have the compositor on, which means anything else is visible at the same time, then this is gonna be triple buffered. Am I using Sway? Yes. So if you triple buffer your game, then you'll get a quadruple buffer in Sway. Huh. Except not, because I actually have Wayland now actually has screen tearing that you can opt into, and it's glorious. Okay. Never thought I would want like the whole reason I switched to Wayland back in 2021. Yeah, I've been using Wayland for like 4 years, by the way. You should have seen it 4 years ago. The whole reason I switched to it was because I couldn't fix my screen tearing and stuttering problems on X11, even with an AMD card. So I just switched to Wayland and it immediately fixed everything. But then I ended up wanting screen tearing to come back, specifically for playing Osu, because VSync adds latency, and a rhythm game you need the least amount of latency possible. But I also fixed that by getting a 180 hertz monitor, and VSync at 180 hertz is fine. So like, yeah, you're good. Okay. This infrastructure is known as swap chain. Yep. Swap chain is essentially a queue of images. Yep. How exactly the queue works and the conditions for presenting an image, or no, our application will acquire such an image to draw to it and then return it to the queue. How exactly the queue works and conditions for presenting an image from the queue depend on how the swap chain is set up, but the general purpose of the swap chain is to synchronize the presentation of images with the refresh rate of the screen. Checking for swap chain support. Not all graphics cards are capable of presenting images directly to a screen for various reasons. This song is loud. That's fine. Not all graphics cards are capable of presenting image directly to screen for various reasons. For example, because they are designed for servers that don't have any display outputs. Secondly, since image presentation is heavily tied into the Windows system, and the services associated with Windows, it is not actually part of the Vulkan core. You have to enable VK KHR swap chain device extensions after querying it for support. Flipboard and Wayland is a nightmare. What do you mean? It works fine. Your mic started to sputter a bit, but it's okay now. Strange. Might have just been me mumbling. For that purpose, we'll first extend isDeviceSuitable function to check if this extension is supported. We've previously seen how to list the extensions that are supported by a VK physical device, so doing that should be fairly straightforward. Okay, this song is so distracting. I'm skipping. For that purpose, we'll first extend isDeviceSuitable We've previously seen how to list the extensions that are supported by VK physical device, so doing that should be fairly straightforward. Note that the Vulkan header file provides a nice macro, VK KHR swap chain extension name, that is defined as VK KHR swap chain. The advantage of using this macro is the compiler will catch misspellings. Yeah, X Wayland and Wayland sync just fine. Like, out of the box for me on its way. So that's strange. You're using Hyperland? Well, here's my advice for Hyperland. Don't. Okay, but anyway, we are going to device extensions. Okay. Oh my gosh, VK KHR device swap chain extension name. There we go. I dislike that this doesn't have a VK layer Chronos validation. No. Yeah, that doesn't have like a constant that I can use. It's annoying. Check device extension support is called from is device suitable. Oh wow, I put these in the wrong place. Constants, types. Whatever. And types. Okay. Okay, so bool check device extension support. Return true. Okay, modify the body of the function to enumerate the extensions and check if all the required extensions are amongst them. Okay, so we unit 32 T extension count. Okay, enumerate device extension properties. Physical device. Oh, device. Oh, there's a name collision, isn't there? Yeah, there's a VK device up here. Logical device. Okay, so device, P layer name, not player name. Okay, and then we do our ye old Cialic. VK extension properties. New game gonna be on Vulkan? I have no idea about a new game or a Vulkan. Okay, Factorio with ray tracing. What's the render of Factorio? OpenGL? Yes. Sorry, I'm currently eating food. Okay, so it wants us to turn the required extensions into a set. Oh, I see. Lock properties. Oh, that's neat. Support multi-threading. Is there a say the properties empty thing? Now. So we need to check if every required extension is in the available extensions. So we're gonna have to do this the slow way. All present equals. Oh wait, we don't want to panic. We want to return false. But we probably want to log. Logging. Okay, cool. And then we need to free available extensions. And there as well. Oh, failed to initialize, failed to find a suitable GPU. Okay, so let's Hmm. DKK swap chain is not found. Oh, okay, so this is available instance extensions, and then this is still required instance extensions. Those are instance extensions, whereas these are device extensions. But why is it doing that twice? Oh, well, I see why it's broken. Okay. There we go. Wow, we have a lot of extensions. Cool. All right. More food. One sec. I think what I don't like about this is the cheese texture. It's unpleasant. You're right, it's probably processed cheese or fake cheese of some kind. Made a resource location struct and impl for my Rust game. Getters removed namespace and path constructor that returns result stuff, resource location error, and validation for allowed characters in the namespace and path. Nice. It's okay. I made a bunch of lines on the console. Ha! Okay. Did that. Doesn't use a set of strings here to represent the unconfirmed required extensions. That way we can easily tick them off while enumerating the sequence of available extensions. Of course, you can also use a nested loop. Performance differences are relevant. Now run the code and verify that your graphics card is indeed capable of creating a swap chain. Should be noted that the availability of a presentation queue, as we checked in the previous chapter, implies that the swap chain extension must be supported. However, it is still good to be explicit about things, and the extension does have to be explicitly enabled. Cool. Using a swap chain requires enabling the VKKHR swap chain extension first. Enabling the extension just requires a small change to the logical device creation. That was an in-device. Check device extension to support. Yeah, okay. Cool. There we go. Cool. So now we're creating a swap chain. Or no, we're getting the swap chain extension. We're gonna be able to create a swap chain. Uh-oh. We still have a long ways to go before we actually create one. Yes, the question mark operator is one of Rust's best features. And there's a reason why other languages have started implementing it, like Zig and C3 and Hair all have it as well, I think. I think C3 has it. Okay, querying details of swap chain support. Just checking if the swap chain is available is not sufficient because it may not actually be compatible with our Windows surface. Of course not. Yes, Dogga Chaos, I'm aware. Creating a swap chain involves a lot more settings than instance and device creation, so we need to query for some more details before we're able to proceed. There are basically three kinds of properties we need to check. Basic surface capabilities, min-max number of images of swap chain, min-max width and height of images, surface formats, pixel color, color space, available presentation mode. Similar to find queue families, we'll use a struct to pass these details around once they've been queried. The three aforementioned types of properties come in the form of following structs and lists of structs. Swap chain support detail. Okay. Happy doggo? Yeah. Okay, so we're gonna need to remember to free all of these vectors or all these arrays in the swap chain support details. Now create a new function, queries swap chain support, that will populate this struct. Okay. Okay, so that'll initialize it all to 0. Yes. Okay, this is gonna need to be up here because I'm pretty sure we're gonna use this in is device suitable. Okay, this section covers how to query the structs that include this information. Meaning of these structs and exactly which data they contain is discussed in the next section. What happened to my music? Done. Wow, I went through all of it. Oh, I hadn't gone through all. Oh no, I just ruined it. Frick. There we go. Okay. Let's start with the basic surface capabilities. These properties are simple to query and are returned in a single VK surface capabilities KHR struct. Cool. Easy. Okay. This function takes specified VK physical device and VK surface KHR window surface into account when determining the supported capabilities. Okay. All of the support querying functions have these two as first parameters because they're the core components of the swap chain. Right? You have your physical device and your surface. That makes sense. The next step is about querying the supported surface formats. Because this is a list of structs, it follows the similar ritual of two function calls. Okay. Actually, I can just throw those in there. Okay, get physical device surface formats KHR. Geez, that's a long name. Device surface. Okay, so what if there's no formats? I feel like we should just error out. Just return nothing. VK surface format KHR. Okay, details.formats equal that. VK get physical device, same thing. There we go. Make sure the vector is resized to hold all available formats. Finally, querying the supported presentation modes works exactly the same way. Surface present mode. There we go. All the details are in the struct now, so let's extend it as device suitable once more. Yep. Number of format pairs supported must be greater than or equal to 1. These service formats must not contain an entry whose value for format is VK format undefined. Oh, so there's always going to be at least one. Is that the same for present modes as well? So the tutorial is telling me to do something I don't need to do. Okay, so I would do it like this, but I assume that we're gonna use these later, and that's why it has us throw them in a vector. Okay. So now we're querying swap chain details, which may or may not actually be necessary, according to Malformed Barracuda. You get present mode FIFO KHR. This is the only value present mode that is required to be supported. Right. I missed what? I was just recapping that we are now selecting a swap chain, or we're now querying if the swap chain is adequate, which you said may or may not actually be required because it's guaranteed to have at least one present format. And at least one present mode. So this whole thing is like useless, basically. Because this is guaranteed to have at least one of each. And I guess like if you say you support a swap chain, but then you don't give any supported formats or present modes, then you're kind of doing something weird. Okay, choosing the right settings for the swap chain. The swap chain adequate conditions were met. then the support is definitely sufficient, but there may still be many different modes of varying optimality. We will now write a couple of functions to find the right settings for the best possible swap chain. There are 3 types of settings to determine: surface format, presentation mode, and swap extent. Okay. For each of these settings, we will have an ideal value in mind that we'll go with if it's available, and otherwise we'll create some logic to find the next best thing. Feels like I could just get the first one and call it good. Well, I don't want to accidentally start at HDR, but I mean, could. HDR triangle, let's go. It might actually be fun to do. Ray traced HDR triangle. Yeah. Okay. So, hold on, gotta finish chewing. Okay, so we're gonna have to pass the formats to this boy. Okay, each VK surface format KHR entry contains a format and a color space member. Format member specifies the color channels and types. For example, BGRA8, sRGB, the color space. So I'm a VK format B16 UNorm, wahaha, HDR. BGRA, BGR and alpha channels in that order with an 8-bit unsigned integer for a total of 32 bits per pixel. Man, it's kind of easy to forget just how much data we're pushing to these screens at every moment. Like, there's 32 bits per pixel. Let's do this math. So there's 32 bits per pixel times 2560 times 1440 times 60. Answer in giga. So that's 7 gigabits that you need in order to push a 1440p image at 60 FPS. 7 times, well, actually, that's 14 times more bandwidth than my internet has. I have a 10 gig connection to my local server, but I only have a 2.5 gig connection on my PC side. So the 10 gig connection, it actually has been used at more than 2.5 gig because I'll be pushing some files to my server at 2.5 gig, and then my brother will start streaming from my Jellyfin server at the same time. So it'll go over 2.5 gig. It's just my way of saying, yes, it was justified to buy a 10 gig SFP adapter for my server. But yeah, 7 gigabits just for regular sRGB. And that can get up to twice as much, right? Yeah, 32 bits per pixel because we have 8 times 4. If we go to 16 times 4, then that's 14, yeah. Exactly double. So if we want a full depth HDR 16 image, then we would have 14 gigabits. Okay, anyway. Color space member indicates if the sRGB color space is supported or not using the VK color space. VK color space. Ah, we have all the things. HDR10. Dolby Vision. So VK color space Dolby Vision EXT is deprecated, but no reason was given in the API XML. Interesting. I mean, I'd be surprised if I was able to implement Dolby Vision, because Dolby Vision is proprietary, not open source. So like, how does that work? And HDR is such a freaking mess, dude. Note that this flag used to be called color space sRGB nonlinear. Oh, so they just added an underscore. That's cool. The color space will use sRGB if it's available because it results in more accurate perceived colors. It is also pretty much the standard color space for images, like the textures we'll use later on. Because of that, we should also use an sRGB color format, of which one of the most common is BGRA8. Okay. So if we go through available formats, oh, I want a const reference, but that's not how that works. Okay, so we have an array there. sRGB and available format color space. Oh, that kind of sucks. I wonder if there's a way to make it say, hey, use Egyptian style braces if there's multiple lines on this if statement. It's fine, I'll just do it like this. Okay. If that also fails, then we can start ranking the available formats based on how good they are, but in most cases, it's okay to just settle with the first format that is specified. Why don't I just do that to begin with? SDL assert's actually really cool, because if I change this to be an assert that will always fail, then it will, wait, oh, I'm not doing this yet, but I'll show you down here. If I just SDL assert 0, 1, 0, then it gives you an assertion fail pop-up, says always ignore, abort, break, or retry. So you can actually, like at this point, you can attach a debugger. A tutorial, copy PID. How do I copy PID? I don't think I can. 1563852. There we go. So you don't have to keep that there, but you can break, and then it'll break there. Isn't that super cool? Super long-winded example. Yeah, or you can just ignore. Yoink. Super nice. After I was like nerding out about that to my coworkers, it was pointed out to me that that's just a built-in feature on Windows. Don't have to use SDL for that. Okay. So it's using the first format. Presentation mode. The presentation mode is arguably the most important setting for the swap chain because it represents the actual conditions for showing images to the screen. There are 4 possible modes in Vulkan. Okay. You can do immediate, FIFO, which is double buffering, I think. Takes an image from the front of the queue. Back of the queue. If the queue is full, then the program has to wait. Yeah. FIFO relaxed. This mode only differs from the previous one if the application is late and the queue was empty on the last vertical blank. Instead of waiting for the next vertical blank, the image is transferred right away when it finally arrives. Huh. Present mode mailbox. This is another variation of the second mode. Instead of blocking the application when the queue is full, the images that are already queued are simply replaced with the newer ones. Oh. This mode can then be used to render frames as fast as possible while still avoiding tearing, resulting in fewer latency issues than standard vertical sync. This is commonly known as triple buffering, although the existence of 3 buffers alone does not necessarily mean that the frame rate is unlocked. Okay. So you could like render at 1000 FPS and it'll just keep replacing them. But then when it flips to the screen, it'll use the most recently submitted frame. Okay, that's cool. Kind of like that. But it might be good to just do immediate because like on Wayland, it enforces VSync by default. So, yeah. Okay, only the VK% left FIFO is guaranteed to be available. Well, like, it knows that it's available. So why are we checking for it up there? I don't know. So we're gonna have to write a function that looks for the best mode that is available. Okay. Okay. Actually, this is just an enum, right? Yeah. We don't need to take a reference to that. So if a mailbox is available, we can do that. Otherwise, we can just return VK present FIFO. Eventually, we might want to do a thing where you can select what it is, but that's fine. Okay. Allows us to avoid tearing while still maintaining a fairly low latency by rendering new images that are as up to date as possible right until the vertical blank. Mobile devices where energy usage is more important, you will probably want to use FIFO instead. Now let's look through the list to see if VK present mode mailbox is available. Okay, we did that. Swap extent. That leaves only one major property for which we'll add one last function. Do swap extent. Okay, the swap extent is the resolution of the swap chain images, and it's almost always exactly equal to the resolution of the window that we're drawing to in pixels. The range of the possible resolutions is defined in the VK surface capabilities KHR structure. Vulkan tells us to match the resolution of the window by setting the width and height in the current extent member. However, some window managers do allow us to differ here, and this is indicated by setting the width and height in current extent to a special value, the maximum value of UN32. In that case, we'll pick the resolution that best matches the window within min image extent and max image extent bounds, but we must specify the resolution in the correct unit. Okay, pixels and screen coordinates, yeah, I know all that already. Okay, we're just gonna copy all this garbage. Oh, that's not an array. Okay, so there's Can I just do this? Yes. Implicit casting, let's go. Is there no clamp in the math library? C clamp function. C language clamp function. And it's only in C++. Oh, I can just use GLM. That works. Nice. Thanks, GLM. Right? Return GLM min, GLM max. Yeah. That's really nice. Thank you. Okay. Oh, that's floats, though. So it's converting all these to floats, and then converting them back to UN32. That's pretty cursed. Whatever. Can you use stood clamp? No, I can't. Why is this all in an else statement? Bad. Okay, there we go. That function is used to bound. Yeah. Create a swap chain. Now that we have all these helper functions assisting us with the choices we have to make our runtime, we finally have all the information that is needed to create a working swap chain. Create a create swap chain function that starts out with the result of these calls, and make sure to call it from init Vulkan after logical device creation. Okay. Create swap chain. I like how there's so much repeated work here, like we're querying swap chain support multiple times and things like that. AHR, surface format. Choose swap surface format. That is a giant struct, right? Hey, it's a decently sized struct. That's 52 bytes. Whatever, we don't need to take a reference to that. Okay, so all of these can actually be thrown down there. Never mind. These choosing functions can, but not query swap chain support. There we go. Aside from these properties, we also have to decide how many images we would like to have in the swap chain. The implementation specifies the minimum number that is required to function. Okay. However, simply sticking to this minimum means that we may sometimes have to wait on the driver to complete internal operations before we can acquire another image to render to. Therefore, it is recommended to request at least one more image than the minimum. But also make sure not to exceed the maximum number of images while doing this, where 0 is a special value, which means there is no maximum. Or we could just use glm min. Wait, no. Then it'll always do 0. As a tradition with Vulkan objects, creating swap chain object requires filling in a large structure. Specifying which surface tied to the deals swap chain images are specified. What is that? Usage color attachment bit. Usage sampled storage, color attachment, depth stencil, transient attachment, input attachment. Wow. If you use a physical vice clamp directly to the motherboard. Yeah, that would go over well. The image array layer specifies the amount of layers that each image consists of. This is always one, unless you are developing a stereoscopic 3D application. Cool. It's cool that it supports that. The image usage bit field specifies what kind of operations we'll use the images in the swap chain for. This tutorial, we're going to render directly to them, which means that they're used as a color attachment. It's also possible that you'll render images to a separate image first to perform operations like post-processing. In that case, it may use a value like transfer DST bit, transfer destination, instead, and use a memory operation to transfer the rendered image to a swap chain image. Right, because that's for like deferred rendering and stuff, where you render to a bunch of frame buffers and then you do post-processing lighting and other effects on those frame buffers. Or at least those buffers, not frame buffers. Okay. Oh, we need to do the Q families things again. Where's the present mode? Did I just miss it? Oh, we haven't done it yet. Yeah, it's down there. Okay, so then we do Q family indices again. Okay, so if indices.graphics family is not equal to indices present family, then we do this. VK sharing mode concurrent. Okay, so create info image sharing. All right, because we need to be able to have. Oh, because two queues could be doing it at the same time. So it needs to add locks and stuff for different threads. The family index count is 2. Create info.p q family indices equals q family indices. Otherwise, it can be exclusive because there's only one thing that's going to be accessing it. Oh, yeah, no, we don't need that. We don't need none of those. Okay, yeah, that makes sense. So let's see if there's any documentation here. No. VK sharing mode. Exclusive specifies that access to any range or image sub-resources of the object will be exclusive to a single queue family, multiple queue families. Right, and it may have lower performance because then it has to make sure that it's not accessing from both at the same time. It has to add locks and things like that, I assume. That makes sense. Next, we need to specify how to handle swap chain images that will be used across multiple queue families. This will be the case in our application. If the graphics queue family is different from the presentation queue, we'll be drawing on the images in the swap chain from the graphics queue and then submitting them on the presentation queue. There are 2 ways to handle images that are accessed from multiple queues. Exclusive, yep. Ownership must be explicitly transferred before using it in another queue family. Ownership can be used across multiple queue families without explicit ownership transfers. Queue families differ, and we'll be using concurrent mode. Avoid having to do the ownership chapters, because those involve some concepts that are better explained at a later time. Current mode requires you to specify in advance between which queue families ownership will be shared using the indices parameter. If the graphics queue family and the presentation queue family are the same, which will be the case on most hardware, we should stick to exclusive mode because concurrent mode requires you to specify at least 2 distinct queue families. Gotcha. Specify, okay, so this is next. Swap chain support .capabilities .current transform. Ah, I see. Rotation and horizontal mirrors, and it's just identity. Okay, inherit. Specify that a certain transform will be applied to the images in the swap chain if it is supported, like a 90-degree clockwise rotation or horizontal flip. To specify that you do not want any transformations, simply specify the current transformation. Composite alpha opaque bit. Inherit opaque post multiplied pre multiplied. Composite alpha field specifies the alpha channel should be used for blending with other windows in the windowing system. You almost always want to simply ignore the alpha channel, hence opaque, right? But if you wanted like a file manager to have like a translucent sidebar, then you'd want to do that. Or you'd want to have a post multiplied probably. Okay, and then present mode is present mode. Oh, this is an int. Huh. Guess I'll do VK true just in case. The present mode member speaks for itself. If the clipped member is set to true, then that means that we don't care about the color of pixels that are obscured. For example, because another window is in front of them. Unless you really need to be able to read those pixels back and get predictable results, you'll get the best performance by enabling clipping. Okay, cool. So like, it will clip if it's covered partially by that, then it'll only draw this part. That's nice. Old swap chain is null. This is one last field. Old swap chain, may as well. With Vulkan, it's possible that your swap chain becomes invalid or unoptimized while your application is running, for example, because the window is resized. In that case, the swap chain actually needs to be recreated from scratch, and a reference to the old one must be specified in this field. This is a complex topic that we'll learn more about in a future chapter. For now, we'll assume that we'll only ever create one swap chain. Okay, so we should probably make sure that we can't resize the window. That is the case. Cool. And now we should be able to run this. We're not actually creating it. Okay, now we can actually create the swap chain. Incredible. The device. Create info. Null. Swap chain. There we go. Let's create a swap chain. We did, and we leaked. We leaked 1.5 kilobytes, 15 kilobytes. Jeez Louise. Okay. Yeah, we are not destroying the swap chain. Cool. No leaks. Parameters of the logical device, swap chain, creation info, yeah. Now run the application, ensure the swap chain is created successfully. If at this point you get an access violation error. Ugh. Okay, Steam overlay layer. Try removing create info image extent equals extent. Okay, so we get an ASAN error as well as a Vulkan error. Invalid. Vulkan spec states image extent members width and height must both be non-zero. That's cool. Man, Vulkan is nice. Okay. Retrieving the swap chain images. Swap chain has been created now, so all that remains is retrieving the handles of the VK images in it. Reference these during rendering operations in later chapters. Add a class member to store the handles. Oh boy. But we can have different numbers depending on which number we decided to have. It's like if we have mailbox, then we have a different number than if we chose FIFA or immediate. So we have to keep VK image, swap chain images. I could probably do an U into 8, honestly, but I'm gonna match Vulkan's. Chain image count equals 0. Okay, so we're gonna have to allocate and reallocate that. If I'm making a serious application in C, I'm probably gonna do like a Vulkan tutorial list, like that VT list type that would encapsulate the data and the length, but I'm not doing that right now. Images were created by the implementation for the swap chain, and they will be automatically cleaned up once the swap chain has been destroyed. Therefore, we don't need to add any cleanup code. But I do need to free that memory. I'm adding the code to retrieve the handles to the end of create swap chain function right after the VK create swap chain KHR call. Retrieving them is very similar to the other times where we retrieved an array of objects in Vulkan, right? At the end of create swap chain, as VK image, right? Yeah. There we go. One last thing. Store the format and the extent we've chosen for the swap chain images and member variables. We'll need them in future chapters. Okay, I might want to wrap this in a struct swap chain info at some point. But for now, it's fine. Okay, that's copied by value from here, right? Yes. Cool. Now I have a set of images that can be drawn onto and can be presented to the window. The next chapter will begin to cover how we can set up the images as render targets, and then we can start looking into the actual graphics pipeline. Frickin' finally. Oh, man. Are we gonna get triangle in this stream? Okay, so we're gonna leak memory. Oh, it didn't complain, actually. Okay, image views. To use any VK image, including those in the swap chain, in the render pipeline, we have to create a VK image view object. An image view is quite literally a view into an image. Okay, easy enough. It describes how to access the image and which part of the image to access. For example, if it should be treated as a 2D texture, depth texture, it's treated as a 2D depth texture without any mapping levels. This chapter will write a create image views function that creates a basic image view for every image in the swap chain, so you can use them as color targets later on. First, add a class member to store the image views in. Swap chain image views. Okay. Okay, first thing we need to do is resize the list to fit all the image views we're creating. Okay. Oh, we can just... There we go. Next cycle loop iterates over all the swap chain images. Parameters for image view creation are specified at VK image view create info. Image equals swap chain images I type view type and format fields specify the image data should be interpreted. View type parameter allows you to treat images as 1D, 2D, or 3D textures and cube maps. Interesting. Don't know how you would use cube maps, but I don't even know what those are. Create info.format, swap chain image format. Fine. Okay, the components field allows you to swizzle the color channels around. For example, you can map all the channels to the red channel for a monochrome texture. You can also map constant values of 0 and 1 to a channel, in which case we'll stick to our default mapping. I'm pretty sure if they didn't make this 0, I'm going to be very mad. Okay, no, it is 0, so we don't even need to do that. The sub-resource range field describes... Hold on. Oh, you can do that. That's funny. That's actually kind of nice. Okay, but anyway, sub-resource range field describes what the image's purpose is and which part of the image should be accessed. Our images will be used as color targets without any mapping levels or multiple layers. Okay, I don't know what most of those mean. You're working on a stereographic 3D application, then you would create a swap chain with multiple layers. You could then create multiple image views for each image representing the views for the left and right eyes by accessing different layers. Oh, so you could create one swap chain image for, yeah, stereoscopic 3D, that's VR. So if you're making a VR game, then you would create a swap chain with 2 layers per image, and then it would display the same image. It would send that one image to the VR headset, but it would display 1 layer in each eye. Okay, that makes sense. Okay, so the image views were created by us. Well, they will be. Unlike images, the images views were explicitly created, so we have to free them. Okay, an image view is sufficient to start using an image as a texture. But it's not quite ready to be used as a render target just yet. That requires one more step in indirection known as a frame buffer. But first we'll have to set up the graphics pipeline. Okay. Oh, we're finally into the place where OpenGL just drops you from the start. Oh. Okay, time for another short break. I'll be back soon. I'm back. Did you miss me? Okay, so we have graphics or presentation. Okay, so let's review. Let's see how much I can remember. So you have to, you have to create a VK instance, which is like the global state. And then from there, you use the instance to enumerate physical devices. Or sorry, no, you use the instance to create a surface based on your windowing system, in our case, SDL. And then you use those things to enumerate your physical devices and select the one that has all the features you need, including the queue families and certain amounts of VRAM if you are Factorio, stuff like that. And then you use that to create a logical device. And then once you have the logical device, you have to create a swap chain, which involves querying a bunch of other things and selecting a presentation mode and a color space and a bunch of other garbage. Once you have a swap chain, you create images to put into the swap chain, and then you create image views so that you can view the images in the swap chain. That's what we've done so far, I think. Did I miss anything? No. Nice. Easy peasy. Only 498 lines of code. Okay, so now we are at the point where OpenGL would just start you. Actually, let's learn OpenGL.com. Getting started. Shaders. Yeah. You get OpenGL, you create a window with GLSL, and then you do hello window. Or sorry, no. You just create a window with GLSL, and then hello triangle. You immediately go into vertex data. So much easier. Ask you a question about Factorio? Depends on the question. Okay, but we're going to be setting up a graphics pipeline that will be configured to draw our first triangle. Okay. So this is going to be about shaders as well as setting up the steps, because I do know that instead of having it be a fixed set of steps, you can skip steps if you want to. Like, we're not going to need tessellation or geometry shaders, so we can probably just remove those. How to silence the loud as F silos? You don't. You make a mod. But they're rockets. They're supposed to be loud. Okay, so you can't really see it, but okay, vertex/index buffer, input assembler, vertex shader, tessellation, geometry shader, rasterization, fragment shader, color blending, frame buffer. Okay, the input assembler collects the raw vertex data and maybe index data as well. Vertex shaders run for every vertex and applies linear algebra transformations to them. And it passes the data down the pipeline. Tessellation shaders allow you to subdivide geometry based on certain rules to increase the mesh quality. This is often used to make surfaces like brick walls and staircases look less flat when they are nearby. Huh, I hadn't heard of those before. Geometry shader is run on every primitive, triangle line point, and it can discard it or output more primitives than came in. This is similar to the tessellation shader, but much more flexible. However, it is not used much in today's applications because the performance is not that good on most graphics cards, except for Intel's integrated GPUs for some reason. The rasterization stage discretizes the primitives and the fragments. These are the pixel elements that they fill on the frame buffer. Any fragments that fall outside the screen are discarded, and the attributes outputted by the vertex shader are interpolated across the fragments. Usually the fragments that are behind other primitive fragments are also discarded here because of depth testing. The fragment shader is invoked for every fragment that survives and determines which frame buffers the fragments are written to and with which color and depth values. It can do this using the interpolated data from the vertex shader, which can include things like texture coordinates and normals for lighting. Color blending stage applies operations to mix different fragments that map this to the same pixel in the frame buffer. Fragments can simply overwrite each other, add up, or be mixed depending on transparency. Stages with a green color are known as fixed function stages. These stages allow you to tweak their operations using parameters, but the way they work is predefined. Input, assembler, rasterization, color blending. But all of these shaders are completely programmable.
Stages with an orange color are programmable, which means that you can upload your own code to the graphics card to apply exactly the operations you want. This allows you to use fragment shaders, for example, to implement anything from texturing and lighting to ray tracers. These programs run on many GPU cores simultaneously to process many objects like vertices and fragments in parallel. Use older APIs like OpenGL, and we're used to being able to change any pipeline setting at will with calls like GL blend function and OM set blend state. I assume that's DirectX. The graphics pipeline in Vulkan is almost completely immutable, so you must recreate the pipeline from scratch if you want to change shaders, bind different frame buffers, or change the blend function. Disadvantage is that you'll have to create a number of pipelines that represent all of the different combinations of states you want to use in your rendering operations. However, because all of the operations you'll be doing in the pipeline are known in advance, the driver can optimize for it much better. Interesting. So if you want to have like draw a triangle and then draw a triangle with additive blending, you have to create two completely separate pipelines for that. Some of the programmable stages are optional based on what you intend to do. For example, the tessellation and geometry stages can be disabled if you are just drawing simple geometry. If you're only interested in depth values, then you can disable the fragment shader, which is useful for shadow map generation. The next chapter will first create the two programmable stages required to put a triangle onto the screen, the vertex and fragment shaders. The fixed function configuration like blending mode, viewport, rasterization will be set up in the chapter after that. The final part of setting up the graphics pipeline in Vulkan involves the specification of input and output frame buffers. Create graphics pipeline. Create graphics pipeline. You know what? We are going to do init Vulkan. Okay, cool. Next. Okay, unlike earlier APIs, shader code of Vulkan has to be specified in bytecode format as opposed to human readable like GLSL or HLSL. SPIR-V, yep. The advantage using bytecode format, yeah, we already explained this. It makes the implementation in drivers a lot easier and more consistent. You don't need to write this bytecode by hand. We can use GLSLC. Pretty sure I already set that up. Yep. So we need to make our shaders. GLSL is a shading language with C-style syntax. Programs written in it have a main function that is invoked for every object. Instead of using parameters for input and a return value as output, GLSL uses global variables to handle input and output. The language includes many features to aid in graphics programming, like built-in vector and matrix primitives. Functions for operations like cross products, matrix vector products, and reflections around a vector are included. Yeah, I already know all that. As the previous chapter mentioned, we need to write a vertex shader and a fragment shader to get a triangle on the screen. The next two sections will cover the GLSL code of each of these, and after that I'll show you how to produce two SPIR-V binaries and load them into the program. Okay. Jeez, why is my throat suddenly dry? Okay, the vertex shader processes each incoming vertex, takes its attributes like world position, color, normal, and texture coordinates as input. The output is the final position and clip coordinates, and the attributes that need to be passed to the fragment shader, like color and texture coordinates. These values will then be interpolated over the fragments by the rasterizer to produce a smooth gradient. You can later look at Niagara playlist from a Roblox dev on Vulkan Toy Engine for testing performance of different features. It's also written in C. There are some gotchas on configuring pipelines. Well, thank you. Click coordinate is a four-dimensional vector from the vertex shader that is subsequently turned into a normalized device coordinate by dividing the whole vector by its last component. These normalized device coordinates are homogeneous coordinates that map the frame buffer to -1 to 1 coordinate system that looks like the following. Yes, because Vulkan actually does it correctly and has positive y down instead of positive y up, like DirectX and Metal do. You should already be familiar with these if you have dabbled in computer graphics before. If you have used OpenGL before, then you'll notice that the sign of the y-coordinate is now flipped. The z-coordinate now uses the same range as it does in Direct 3D from 0 to 1 instead of -1 to 1. Okay. For our first triangle, we won't be applying any transformations. We'll just specify the positions of the 3 vertices directly as normalized device coordinates to create the following shape. Okay. You can directly output normalized device coordinates by outputting them as clip coordinates in the vertex shader with the last component set to 1. That way, the division to transform clip coordinates to normalized device coordinates will not change anything. Normally, these coordinates would be stored in a vertex buffer. But creating a vertex buffer in Vulkan and filling it with data is not trivial. Therefore, I've decided to postpone that until after we've had the satisfaction of seeing a triangle pop up on the screen. We're going to do something a little unorthodox in the meanwhile, including the coordinates directly in the vertex shader. Right, because -y is up now. Vertex index. And the main function is invoked for every vertex. The built-in GL vertex index variable contains the index of the current vertex. This is usually an index into the vertex buffer, but in our case, it will be an index into a hard-coded array of vertex data. Position of each vertex is accessed from the constant array in the shader and combined with the dummy Z and W components produce a position and clip coordinates. The built-in variable GL position functions as the output. There we go. Fragment shader. Yep, fills in the fragments, simple fragment shaded, outputs color red for the entire triangle. Main function is called for every fragment, just like the vertex shader main function is called for every vertex. Colors in GLSL are 4-component vectors with the RGB and alpha channels within the 0 to 1 range. Unlike GL position, there's no built-in variable to output a color for the current fragment. To specify your own output variable for each frame buffer, where the layout location equals 0, specifies the index of the frame buffer. Oh. Color red is written to this out color variable that is linked to the first and only frame buffer at index 0. Okay, so if you wanted, you could write to multiple frame buffers at the same time by doing this. That's kind of neat. Okay, but we want per vertex colors, so we're going to do that. Wait, why are these? Oh, it's not different. There we go. Now we just need to pass these per vertex colors to the fragment shader that can output their interpolated values. Add an output for color to the vertex shader and route it to the main function. Oh, that's in the vertex shader. Right, that makes sense. There we go. Input variable does not necessarily have to use the same name, but they will link together using the indices specified by the location directives. Okay, that makes sense, because, like, yeah, for every vertex, it writes to a frame buffer, and then, yeah, okay. Yeah, they'll be interpolated. Okay. Compiling the shaders. Linking multiple files not supported yet. Use C to compile files individually. Syntax error expected right paren. Oh, it doesn't support trailing commas. There we go. Oh, I put them in here. I can't set the output directory. There we go. If your shader contains a syntax error, then the compiler will tell you the exact line number and problem that as you would expect. Yeah, compiling shaders in the command line is one of the most straightforward options, and it's the one that we'll be using in this tutorial. But it's also possible to compile shaders directly from your own code. The Vulkan SDK includes a libshaderc, which is a library to compile GSL code to SPIR-V from within your program. Maybe I'll look at that later. Okay, loading a shader. I am not using any of that. That's null terminated, I think, so it should be fine. Okay. Make sure that the shaders are loaded correctly by printing the size of the buffers and checking if they match the actual file size in bytes. They do, because SDL load file will work fine, except SDL safe. Oh, that's... I guess that's why they put them on the right, but that's still annoying. Before we can pass the code to the pipelines, we have to wrap it in a VK shader module object. So let's create a helper function, create shader module to do just that. Function will take a buffer with the bytecode as parameter and will create a VK shader module from it. Creating shader module is simple. We only need to specify a pointer to the buffer with the bytecode and the length of it. This information is specified in a VK shader module create info structure. I could just use strlen, but I don't like using null terminated strings. Okay, shader module is simple. Code size equals code length. That's dumb. Vertex shader code size is undefined. It should be 0. Oh! I didn't know that was a thing. Huh. I was trying to do it in Lua style. Interestingly, you don't have to specify the type or anything. The shader module is just the shader module. Just the shader. Ugh. Okay, I assume that I can then free these things. I'm gonna try it. So if I can, then I'm just gonna rewrite that function to take a file path. It should then happen at the end of this function by adding 2 calls to VK destroy shader module. What? Oh, okay. Clear stage creation.
Okay, so I am going to what size of VK shader module create info must be a multiple of 4? Oh, I read over this. One catch is that the size of the bytecode is specified in bytes. The bytecode pointer is a uint32t pointer rather than a car pointer. Therefore, we need to cast the pointer to the interpret cast. When you perform a cast like this, you also need to ensure that the data satisfies the alignment requirements of uint32. Well, I guess that does make sense to be a uint32t. Because that's how the... There, I figured it out. Actually, that's good then that we are taking the size, because this size does not include the null terminator, so it'll be good. Otherwise, it would have been one. If we use Stirline, it would have been one too many. Or does Stirline include the null terminator? I always forget. No, it does not count the number of characters in the array. Not include the null character. Okay, that's what I thought. Actually, it wasn't what I thought. I love C. Shader stage creation. To actually use the shaders, we'll need to assign them to a specific pipeline stage through VK pipeline shader stage create info structures as part of the actual pipeline creation process. We'll start by filling in the structure for the vertex shader, again in the create graphics pipeline function. Oh wow, there's a lot of those. They have Raygen, which I assume is ray tracing stage. And that's in the fragment shader though. First step, besides the obligatory S-type members telling Vulkan which pipeline stage the shader is going to be used, there's an enum value for each of the programming stages described in the previous chapter. Then module, vert shader module. The name equals main. Specify the shader module containing the code and the function to invoke, known as the entry point. It means that it's possible to combine multiple fragment shaders into a single shader module and use different entry points to differentiate between their behaviors. In this case, we'll stick to the standard main. That's interesting. There's one more optional member, P specialization info, which we won't be using here, but is worth discussing. It allows you to specify values for shader constants. You can use the single shader module where its behavior can be configured at pipeline creation by specifying different values for constants used in it. I see. This is more efficient than configuring the shader using variables at render time because the compiler can do optimizations like eliminating if statements that depend on these values. If you don't have any constants like that, then you can set the member to null pointer, which our struct initialization does automatically. Okay, so it takes in spurv bytecode and it compiles that even more. Huh. Depending on what you do. Modifying the structure to suit the fragment shader is easy.
Okay. Finish by defining an array that contains these two structs, which we'll later use to reference them in the actual pipeline creation step. Okay. All there is to describing the programmable stages of the pipeline. In the next chapter, we'll look at the fixed function stages. Okay, so you can define them in any order. We're gonna try this. And it'll just organize them depending on their stage, I assume. Oh yeah, of course, we're not freeing these. Okay, the older graphics APIs provide a default state for most of the stages. Right, because I remember in the OpenGL tutorial, we didn't add our shaders until later. You can add, you can make a triangle without shaders. It'll just have defaults. In Vulkan, you have to be explicit about most pipeline states, as it'll be baked into an immutable pipeline state object. This chapter will fill in all of the structures to configure these fixed function operations. Dynamic state. While most of the pipeline state needs to be baked into the pipeline state, a limited amount of the state can actually be changed without recreating the pipeline at draw time. Examples are the size of the viewport, line width, and blend constants. Oh, okay. If you want to use the dynamic state and keep these properties out, then you'll have to fill in a VK pipeline dynamic state create info structure like this. Will cause the configuration of these values to be ignored, and you will be able and required to specify the data at drawing time. This results in a more flexible setup and is very common for things like viewport and scissor state, which would result in a more complex setup when being baked into the pipeline state, right? Because every time you resize the window, you'd have to recreate all your pipelines. So yeah. My throat's getting dry. Been talking for 6 hours. Vertex input. The VK pipeline vertex input state create info structure describes the format of the vertex data that will be passed to the vertex shader. Describes this in roughly 2 ways. Bindings, spacing between data, and whether the data is per vertex or per instance. Right. Attribute descriptions. Types of attributes you pass into the vertex shader, which binding to load them from, and at which offset. Because we're hardcoding the vertex data directly into the vertex shader, we'll fill in this structure to specify that there is no vertex data to load for now. We'll get back to it in the vertex buffer chapter. Okay, I'm getting a little impatient. We're going to copy.
Okay, that's pretty familiar looking. P vertex binding descriptions and P vertex attribute descriptions members point to an array of structs that describe the aforementioned details for loading vertex data. Add the structure to the create graphics pipeline function right after the shader stages array. Input assembly. The VK pipeline input and assembly state create info struct describes two things: what kind of geometry will be drawn from the vertices, and if primitive restart should be enabled. Former is specified in the topology member and can have values like. Hold on 1 second. Mind me just standing up. Much netter. Sorry, just eating a snack real quick. Okay. Hold on. Gosh dang it. Okay, assembly state create info struct describes two things. Oh, you're gonna go now. Sleep's waiting for you. Well, thanks. My triangle is probably still at least another hour away, if not more. I want to get it done though. I'm not ending the stream till I have a triangle. Hey, B. Jonas. Yes, I mean the graphics library. We are 6 hours in, and we're about 3/5 of the way to a triangle. Okay, so this is where you get your point list, line strip, yeah. Normally the vertices are loaded from the vertex buffer by an index in sequential order, but with an element buffer, you can specify the indices to use yourself. This allows you to perform optimizations like reusing vertices. If you set the primitive restart enable member to VK true, then it's possible to break up lines and triangles in the strip topology modes by using a special index of 0xFFFF or FFFFF. We intend to draw triangles throughout this tutorial, so we'll stick to the following data for the structure. More copy paste, because I'm done typing. Okay. I'm gonna get triangle list and primitive restart enable. Viewports and scissors. A viewport basically describes the region of the frame buffer that the output will be rendered to. This will almost always be 0, 0 to width height, and this tutorial will also be the case. Okay. Gosh, there's so many things to specify. Oh, interesting that the width and height of the viewport are in floating point. Wait, does that mean you can set it to -1 to 1, like OpenGL? Remember that the size of the swap chain and its images may differ from the width and height of the window. The swap chain images will be used as frame buffers later on, so we should stick to their size. The min depth and max depth values specify the range of depth values to use for the frame buffer. These values must be within 0 to 1, okay, but min depth may be higher than max depth. What? If you aren't doing anything special, then you should stick to 0 and 1. While viewports define the transformation from the image to the frame buffer, scissor rectangles define in which regions pixels will actually be stored.
Any pixels outside the scissor rectangles will be discarded by the rasterizer. They function like a filter rather than a transformation. The difference is illustrated below. I see. Note that the left scissor rectangle is just one of the many possibilities that would result in that image, as long as it's larger than the viewport. So if we want to draw an entire frame buffer, we'd specify a scissor rectangle that covers it entirely. Viewports and scissor rectangles need to be specified as static part of the pipeline or as dynamic state set in the command buffer. While the former is more in line with the other states, it's often convenient to make viewport and scissor state dynamic. This gives you a lot more flexibility. This is very common, and all implementations can handle this dynamic state without a performance penalty. When opting for dynamic viewports and scissor rectangles, you need to enable the respective dynamic states for the pipeline. Pretty sure we already did that? Yeah. What? Yeah, it's doing that again. That's weird. I think that's a typo. It's a mistake. And then you only need to specify the count of pipeline creation time. Okay. Actual viewports and scissor rectangles will then later be set up at drawing time. Okay, so these I didn't actually need to do. They can just go away. Without dynamic state, the viewport and scissor rectangle need to be set in the pipeline using the, viewport state create info struct. Oh, I see. So you just keep the viewport as null, and then it just works. Okay. Oh, actually, no. You're also determining the dynamic state. Okay. Independent of how you set them, it is possible to use multiple viewports and scissor rectangles on some graphics cards, and so the structure members reference an array to them. Using multiple requires enabling a GPU feature. Okay. All right, I do need to take a quick break. I'll be back. Okay. Triangle. Rasterizer. Rasterizer takes the geometry that is shaped by the vertices from the vertex shader and turns it into fragments to be colored by the fragment shader. Cool. Also performs depth testing, face culling, and the scissor test. And it can be configured to output fragments that fill entire polygons or just the edges. Wireframe rendering. All this is configured using VK pipeline rasterization state create info. Hold on, was that it wasn't. It was just coincidence. Depth clamp enable equals VK false. Yeah, depth clamp enable set to VK true, then the fragments that are beyond the near and far planes are clamped to them as opposed to discarding them. This is useful in some special cases like shadow maps. Using this requires enabling a GPU feature. Rasterization, rasterizer, discard, enable. I assume that discards fragments that are out of the viewport. Rasterizer discard enables set to VK true, then geometry never passes through the rasterizer stage. Basically disables any output to the frame buffer. Huh. Interesting. Why would you want to do that? Okay, that's pretty self-explanatory. Line point. Oh, you can do points. Fill rectangle NV. Oh gosh, it's lagging so hard. Okay. Polygon mode determines how fragments are generated for geometry. The following modes are available. Fill, line point. Using any mode other than fill requires enabling a GPU feature. Okay. So I assume if we wanted to enable a GPU feature, then we would have to do that during logical device creation. Yes, go green, and I still don't have a triangle. Okay, we're getting there though. Line width is 1. Ooh, we can just change that. No, straightforward. Describes the thickness of lines in terms of number of fragments. The maximum line width that's supported depends on the hardware, and any line thicker than 1.0 requires you to enable the wide lines GPU feature. Okay, cull mode. Okay, cull mode back. So you can do front culling or back culling. Okay, front face. Okay, front face clockwise. Currently deciphering someone else's GUI code? Oh man. I am sorry. This specifies the vertex order for faces to be considered front facing and can be clockwise or counterclockwise. Okay. Depth bias enable. Okay, false. Depth bias constant factor. Oh. We can just ignore all these. It's also, yeah. Rasterizer can alter the depth values by adding a constant value or biasing them based on the fragment's slope. This is sometimes used for shadow mapping, but we won't be using it. Cool. Multi-sampling. VK pipeline multi-sample state create info. Okay, no, I am. Those are all optional. Min sample shading. And thanks to structure giving me some troubles. Sample shading enable. Okay. one of the ways to perform anti-aliasing. It works by combining the fragment shader results of multiple polygons that rasterize to the same pixel. This mainly occurs along edges, which is also where the most noticeable aliasing artifacts occur. Because it doesn't need to run the fragment shader multiple times if only one polygon maps to a pixel, significantly less expensive than simply rendering to a higher resolution and downscaling. Enabling it requires enabling a GPU feature. Revisit multi-sampling in a later chapter. For now, let's keep it disabled. Okay. Depth and stencil testing. If you're using depth and or stencil buffer, then you also need to configure the depth and stencil tests using the info. We don't have one right now, so we can simply pass a null pointer instead of a pointer to such a struct. We'll go back to it in the depth buffering chapter. Depth buffering. Color blending. After a fragment shader has returned a color, it needs to be combined with the color that is already in the frame buffer. This transformation is known as color blending, and there are two ways to do it. Mix the old and new value, combine the old and new value using bitwise operations. There are two types of structs that configure color blending. First struct, color blend attachment state, contains the configuration per attached frame buffer, and the second struct, color blend state create info, contains the global color blending settings. And in our case, we only have one frame buffer. Okay, so you can't change the blending mode on the fly? You have to create a whole new pipeline for that? That kind of blows. This per frame buffer struct allows you to configure the first wave color blending. The operations that will be performed are best demonstrated using the following pseudocode. If blend enable, yeah. Speedrun community. Didn't say the depth bias bool was optional. Well, it is optional because VK false is 0. And this initializes everything else to 0, so we're good. We could also remove these, and it would be fine, but I'm just going to keep them. Color blend struct has no S type. It's true. Yeah, it doesn't. Huh. Weird. I'm on for lockout bingo, and I volunteered to do auto detection for task completion. Now I'm making the rounds on a couple of things. As I thought you were doing work stuff. Oh wow, there's so many blending modes. Jeez Louise. Who does work stuff? Exactly. I didn't work at all today. I've spent all day on this instead. Blend enable set to VK false, a new color from fragment shaders passed through modified. Yeah. Most common way to use color blending is to implement alpha blending, which we want the new color to be blended with the old color based on its opacity. Yeah. It can be accomplished with the following parameters. Yeah, that does kind of stink though, because that does mean I have to create a separate graphics pipeline just to change the wait, hold on. Maybe not. Maybe it's dynamic. Hold on. Blend constants. Ooh, maybe you don't have to recreate the whole pipeline. Okay, you can find all the possible operations of VK blend factor and VK blend op enumerations in the specification. Second structure references an array of structures for all the frame buffers and allows you to set blend constants that you can use as blend factors in the aforementioned calculations. Gosh, there's so much to do here. VK pipeline color blend state. Create info. If you want to use the second method of blending, bitwise combination, then you should set logic op enable to VK true. The bitwise operation can then be specified in the logic op field. Note that this will automatically disable the first method, as if you had set blend enable to VK false for every attached frame buffer. The color right mask will also be used in this mode to determine which channels in the frame buffer will actually be affected. It is also possible to disable both modes, as we've done here, in which case the fragment colors will be written to the frame buffer unmodified. Okay. Pipeline layout. Oh gosh, we're almost there. You can use uniform values and shaders, which are globals similar to dynamic state variables that can be changed at drawing time to alter the behavior of your shaders without having to recreate them. They are commonly used to pass the transformation matrix to the vertex shader or create texture samplers in the fragment shader. These uniform values need to be specified during pipeline creation by creating a VK pipeline layout object. Even though we won't be using them until a future chapter, we are still required to create an empty pipeline layout. Create a class member. Oh. Okay. And then create the object in the create graphics pipeline function. Yeah, I've stopped typing all of this manually. I want to get a triangle. I am starting to get impatient. Yep. Okay. And then we need to destroy it later. Okay. Structure also specifies push constants, which are another way of passing dynamic values to shaders that we may get into a future chapter. Okay, so that's the thing that you can do later. The pipeline layout will be referenced throughout the program's lifetime, so it should be destroyed at the end. That's it for all the fixed functions state. It's a lot of work to set all of this up from scratch, but the advantage is that now we're nearly fully aware of everything that is going on in the graphics pipeline. This reduces the chance of running into unexpected behavior, because the default state of certain components is not what you expect. There is, however, one more object to create before we can finally create the graphics pipeline, and that is a render pass. Okay, so this is what Malformed Barracuda said. There's an easier way to do this now. But this doesn't seem that bad, so we're just gonna do it this way. Before we can finish creating the pipeline, we need to tell Vulkan about the frame buffer attachments that will be used while rendering. We need to specify how many color and depth buffers there will be, how many samples to use for all of them, and how their content should be handled throughout the rendering operations. All of this information is wrapped in a render pass object, for which we'll create a new create render pass function. Calls function from init Vulkan before create graphics pipeline. Create render pass. Okay, Attachment description. In our case, we'll just have a single color buffer attachment represented by one of the images from the swap chain. Okay, so 1, 2, 4, 8, 16, 0, 64. So that's how you do multi-sampling, maybe? The format of the color attachment should match the format of the swap chain images, and we're not doing anything with multi-sampling yet, so we'll stick to one sample. Cool. Load op, VK attachment load op clear. Makes sense. Store op equals VK attachment store op store. Store op store, don't care, none KHR, num QCOM. Huh, weird. Load op and store op determine what to do with the data in the attachment before rendering and after rendering. We have the following choices for load op. We can load, serve the existing contents clear. We can clear the values to a constant. Don't care, existing contents are undefined. We don't care about them. Can you collapse functions / scopes in Cocoon? No, you can't. Cocoon does not implement code folding. In our case, we're going to use the clear operation to clear the frame buffer to black before drawing a new frame. There are only two possibilities for store op. You can store or don't care. Cool. We're interested in seeing the render triangle to screen, so we're going to store operations here. Stencil load op. Load op and store op apply. Hold on. Oh, I do have to specify these. Okay, load op and store op. Apply to color and depth data, and the stencil load op, stencil store op, apply to stencil data. Our application won't do anything to stencil buffers, so the results of loading and storing are irrelevant. Initial layout. VK image layout undefined. Really. Final layout. Okay, image layout. Present source KHR. Textures and frame buffers in Vulkan are represented by VK image objects with a certain pixel format. However, the layout of pixels in memory can change based on what you're trying to do with an image. Some of the most common layouts are color attachment optimal, used as color attachment, present source KHR, images to be presented to the swap chain, or transfer destination optimal, images to be used as a destination for a memory copy operation. So if you're like creating a, if you're transferring a texture, then you would create a color attachment with transfer destination optimal. We'll discuss this topic more in depth in the texturing chapter. Yep, I knew it. But what's important to know right now is that images need to be transitioned to specific layouts that are suitable for the operation that they are going to be involved in next. The initial layout specifies which layout the image will have before the render pass begins. Final layout specifies the layout to automatically transition to when the render pass finishes. Using VK image layout undefined for initial layout means that we don't care what the previous layout the image was in. The caveat of this special value is that the contents of the image are not guaranteed to be preserved, but that doesn't matter since we're going to clear it anyways. We want the image to be ready for presentation using the swap chain after rendering, which is why we use the present source KHR final layout. Okay. Subpasses and attachment references. A single render pass can consist of multiple subpasses. Subpasses are subsequent rendering operations that depend on the contents of frame buffers in previous passes. For example, a sequence of post-processing effects that are applied one after another. If you group these rendering operations into one render pass, then Vulkan is able to reorder the operations and conserve memory bandwidth for possibly better performance. For our very first triangle, however, we'll stick to a single subpass. Every subpass references one or more of the attachments that we've described using the structure in the previous sections. These references are themselves VK attachment reference structs that look like this. I think I'm starting to lose track of what's happening here. I'm just reading words now. I've been doing this for too long. But I want a triangle! If I really want a triangle, I would just stop reading entirely and just copy paste. Color attachment optional. The attachment parameter specifies which attachment to reference by its index in the attachment descriptions array. Okay. Our array consists of a single VK attachment description. Its index is 0. The layout specifies which layout we'd like the attachment to have during a subpass that uses this reference. Okay. Automatically transition the attachment to this layout when the subpass is started. We intend to use this attachment to function as a color buffer. The VK image layout color attachment optimal layout will give us the best performance, as its name implies. Subpass is described using a VK subpass description structure. Graphics compute, okay. Graph AMDX. Ray tracing. Huh. Subpasses equals the different shader stages? No, I think subpasses are different passes of the same stage. So like, for example, if you're doing post-processing effects, all of those effects are going to be fragment shaders, but they might need to be run in a certain order, and they might take as input the output from the previous pass of the fragment shader. So you might load your fragment shaders, and then you'll do multiple render passes, and it'll switch which entry point or shader it's using for each one, but it's still in the fragment pass, I think. I think that's what it's saying. Vulkan may also support compute subpasses in the future. It actually does now. So we have to be explicit about this being a graphics subpass. Yep, it does compute, and ray tracing, and subpass shading. Huawei. Huh. Next, specify the reference to the color attachment. Color attachments count equal 1. Color P color attachments equals color attachment. Right. The index of the attachments in this array is directly referenced from the fragment shader with layout location 0 outback 4 outcolor directive. Okay. I see. So we could attach we could have multiple attachments, and then it would have to match in our fragment shader. Following other types of attachments can be referenced by a subpass. The input attachments that are read from a shader. P resolve attachments used for multi-sampling color attachments. Depth stencil and preserve attachments. Which data must be preserved. Render pass. Now that the attachment and basic subpass referencing it have been described, we can create the render pass itself. Create a new class member variable to hold the VK render pass object right above the pipeline layout variable. Interesting that you create the render pass like at the start. Because in SDL GPU, you would begin and end a render pass during your drawing. Render pass object can then be created by filling in the VK render pass create info. Okay. Geez, that's a lot of work. Okay. Well, at least this function is actually not that long, but it's a lot to know. Destroy pipeline layout, destroy render pass. Cool. Just like the pipeline layout, the render pass will be referenced throughout the program, so you should only be cleaned up at the end. That was a lot of work, but in the next chapter, it all comes together to finally create the graphics pipeline. Frickin' finally. We can now combine all the structures and objects from the previous chapters to create the graphics pipeline. Here are the types of objects we have now as a quick recap. Shader stages. Shader modules define the functionality of programmable stages of the graphics pipeline. Fixed function state. All of the structures that define the fixed function stages of the pipeline, like input assembly, rasterizer, viewport, and color blending. Right, so you set state on those. Pipeline layout, the uniform and push values represented by this shader that can be updated at draw time. Render pass, the attachments referenced by the pipeline stages and their usage. All of these combined fully define the functionality of the graphics pipeline. You can now begin filling in the VK graphics pipeline create info. Okay, we start by referencing the array of VK pipeline shader stage create info structs. Jeez Louise. Okay, no, I am freaking copying this. Then we reference all the structures describing the fixed function stage. That comes to pipeline layout, which is a Vulkan handle rather than a struct pointer. Then the render pass equals render pass. Subpass equals 0. Finally, we have the reference to the render pass and the index of the subpass where this graphics pipeline will be used. It is also possible to use other render passes with this pipeline instead of this specific instance, but they have to be compatible with render pass. I don't know what that means. The requirement for compatibility are described here, but we won't be using that feature in this tutorial. Okay, so why'd you tell me about it? Base pipeline handle, VK, no. Base pipeline index. There are actually two more parameters, base pipeline handle, base pipeline index. Vulkan allows you to create a new graphics pipeline by deriving one from an existing pipeline. The idea of a pipeline derivatives is that it is less expensive to set up pipelines when they have much functionality in common with an existing pipeline, and switching between pipelines in the same parent can also be done quicker. Okay, so if I wanted to, say, have my sprite pipeline, and then I wanted a sprite pipeline with additive blending, and then another sprite pipeline with multi-sampling, then I could base both of those other two on the base sprite pipeline, so I don't have to define all this garbage over again. That's nice. You need to specify the handle of existing pipeline, or reference another pipeline that is about to be created by index. Right now there is only a single pipeline, so we'll simply specify a null handle and an invalid index. These values are only used if the VK pipeline create derivative bit flag is also specified in the flags field of VK graphics pipeline create info. Now prepare for the final step by creating a class member to hold the VK pipeline object. Frickin' finally. VK create pipeline. OP inheritance of graphics pipelines? Actually, yes. That is correct. VK create graphics pipelines function actually has more parameters than the usual, designed to take multiple objects and create multiple VK pipeline objects in a single call. The second parameter, for which we've passed VK null handle, references an optional VK pipeline cache. Pipeline cache can be used to store and reuse data relevant to pipeline creation across multiple calls to create pipelines, and even across program executions if the cache is stored in a file. This makes it possible to significantly speed up pipeline creation at a later time. We'll get into this in the pipeline cache chapter. Chat, you know what that means? That is what the compiling Vulkan shaders step in Steam does. It creates a file that has a pipeline cache that pre-computes all of it for you. Crazy. Now the question is, it also compiles Vulkan shaders for Factorio. But Factorio does not use Vulkan, so what's the point? What's it doing? Okay. Now run your program to confirm that all this hard work has resulted in a successful pipeline creation. Oh boy. Vulkan spec states, okay, p create infos, p stages 0, module invalid vk shader module object. Oh. There we go. There's also background processes that compile shaders when you're not playing any games after updates. Those are going to need quite a bit of performance. Yeah. Next couple of chapters will set up the actual frame buffers from the swap chain images and prepare the drawing commands. Okay, how much is left? Gosh. Oh gosh. Okay, we can do it. I'm not going to retain most of this, but we're going to have a working triangle before I finish this freaking stream. But I'm definitely not retaining like 90% of what I'm learning today, because I'm going too quickly. Fortunately, I feel like a lot of this is boilerplate that you don't necessarily need to have memorized, because you only do it like once. So I don't need to feel bad about having to reference guides or something if I have to do this again. Okay. We talked a lot about frame buffers in the past few chapters, and we've set up the render pass to expect a single frame buffer with the same format as the swap chain images. We haven't actually created any yet. The attachments specified during render pass creation are bound by wrapping them into a VK frame buffer object. A frame buffer object references all of the VK image view objects that represent the attachments. In our case, that will only be a single one, the color attachment. Hold on, I didn't retain that sentence. The attachments specified during render pass creation are bound by wrapping them into a VK frame buffer. Okay, so the attachments are like attaching to shaders. Okay. Frame buffer object references all of the VK image view objects that represent the attachments. In our case, that will only be a single one, the color attachment. However, the image that we have to use for that attachment depends on which image the swap chain returns when we retrieve one per presentation. That means we have to create a frame buffer for all of the images in the swap chain and use the one that corresponds to the retrieved image at drawing time. Okay. Oh, I should Oh. Create the objects for this array in a new function. Create frame buffers. Okay. Start by resizing the container to hold all the frame buffers. Okay, easy enough. We'll then iterate through the image views and create frame buffers from. Yeah, I am copying this. Okay. As you can see, creation of frame buffers is quite straightforward. Okay, so let's actually read this. Frame buffer info. We attach the render pass. Attachment count is 1. Attachments equals attachments. Yeah, so we just attach the image view into the frame buffer. And then we set the width and height, and there's 1 layer. Okay. Creation of frame buffer is quite straightforward. You'll need to specify with which render pass the frame buffer needs to be compatible. Yeah. You can only use a frame buffer with the render passes that is compatible with, which roughly means that they will use the same number and type of attachments. The attachment count and p-attachments parameter specifies the VK image view objects that should be bound to the respective attachment descriptions in the render pass p-attachment array. Okay, I think I'm gonna have to re-figure out all of these attachment things later. The width and height are self-explanatory, and layers refers to the number of layers in image arrays. Our swap chain images are single images, so the number of layers is 1. We should delete the frame buffers before the image views and render pass they are based on, but only after we finish rendering. Now reach the milestone where we have all the objects that are required for rendering. In the next chapter, we're going to write the first actual drawing commands. Okay, we're getting there. Ugh. Oh, that mac and cheese made me feel kind of weird. Probably going to throw the rest of it away. Don't feel so good. Commands in Vulkan, like drawing operations and memory transfers, are not executed directly using function calls. You have to record all of the operations you want to perform in command buffer objects. The advantage of this is that when we are ready to tell Vulkan what we want to do, all of the commands are submitted together, and Vulkan can more efficiently process the commands since all of them are available together. In addition, this allows command recording to happen in multiple threads. Awesome. We could split Factorio rendering by chunk or something. I don't know. I have no idea how any of that works. Command pools. We have to create a command pool before we can create command buffers. Command pools manage the memory that is used to store the buffers, and command buffers are allocated from them. Add a new class member to VK command pool. And create a new function, create command pool. So we would get layering issues at chunk borders? Yes. Command pool creation only takes 2 parameters. Possible flags for command pools. Transient. Hint command buffers are re-recorded with new commands very often. Allow new command buffers to be re-recorded individually. Without this flag, they will all have to be reset together. We'll be recording a command buffer every frame, so we want to be able to reset and re-record over it. Thus, we need the set VK command pool create reset command buffer bit. Flag bit for our command pool. Command buffers are executed by submitting them on one of the device queues, like the graphics and presentation queues we retrieved. Each command pool can only allocate command buffers that are submitted on a single type of queue. We're going to record commands for drawing, which is why we've chosen the graphics queue family. Okay. Finish creating the command pool using VK create command pool function. Doesn't have any special parameters. Commands will be used throughout the program. Draw things on the screen, so the pool should only be destroyed at the end. Okay. Command buffer allocation. We can now start allocating command buffers. Create a VK command buffer object as a class member. Command buffers are allocated with VK allocate command buffers function, which takes a VK command buffer allocate info struct as a parameter, specifies the command pool and number of buffers to allocate. Oh, you got primary and secondary command buffers. Okay. Interesting that this doesn't take an allocator. Weird. I guess because you are you allocate the command pool, and then the command pool internally manages the command buffers. Maybe. Well, no, this isn't even taking the pool. Yes, it is. Command pool right there. The level parameter specifies if the allocated command buffers are primary or secondary command buffers. Primary can be submitted to a queue for execution, but cannot be called from other command buffers. Cannot be submitted directly, but can be called from the primary command buffers. Okay. We won't make use of the secondary command buffer functionality here, but you can imagine that it's helpful to reuse common operations from primary command buffers, I guess. As we are only allocating one command buffer, the command buffer count parameter is just 1. Okay. Now start working on the record command buffer function that writes the commands we want to execute into a command buffer. The VK command buffer used will be passed in as a parameter, as well as that index of the current swap chain image we want to write to. We always begin recording a command buffer by calling VK begin command buffer. The small VK command buffer begin info structure as an argument specifies some details about the usage of this specific command buffer. Okay. Flex parameter specifies how we're going to use the command buffer. The following values are available. One-time submit. The command buffer will be re-recorded right after executing it once. Render pass continue. This is a secondary command buffer that will be entirely within a single render pass. Simultaneous use. The command buffer can be resubmitted while it is already pending execution. None of these flags are applicable to us right now. The inheritance info parameter is only relevant for secondary command buffers. It specifies which state to inherit from the calling primary command buffers. It is OOP. If the command buffer was already recorded once, then a call to VK begin command buffer will implicitly reset it. It is not possible to append commands to a buffer at a later time. If a command buffer was already recorded once, then a call to VK begin command buffer will implicitly reset it. Okay, let's see. Starting a render pass. Drawing starts by beginning the render pass with VK command begin render pass. Okay. First parameters of the render pass itself and the attachments to bind. We created a frame buffer for each swap chain image where it is specified as a color attachment. Thus, we need to bind the frame buffers for the swap chain image we want to draw to. Using the image index parameter, which was passed in, we can pick the right frame buffer for the current swap chain image. Render pass info. And next to parameters, define the size of the render area. Easy enough. Render area defines where the shader loads and stores will take place. Pixels outside this region will have undefined values to match the size of the attachments for best performance.
Huh, that's like a union of... Interesting, okay. So you can clear multiple times? Block on 100% opacity, okay. Okay, the render pass can now begin. All the functions that record commands can be recognized by their VK command prefix. They all return void, so there'll be no error handling until we finish recording. The first parameter for every command is always the command buffer to record the command to. The second parameter specifies the details of the render pass we've just provided. Final parameter controls how the drawing commands within the render pass will be provided. I have one of two values. Inline, the render pass commands will be embedded in the primary command buffer itself, and no secondary command buffers will be executed. Secondary command buffers, the render pass commands will be executed from secondary command buffers. Cool. I still don't know what that means. Basic drawing commands. Now bind the graphics pipeline. And that also has no error handling. Second parameter specifies if the pipeline object is a graphics or compute pipeline, and a bunch of other things. Compute, execution graph, AMDX, ray tracing, subpass shading, ray tracing NV. So there's a few things. Noted in the fixed functions chapter, we did specify viewport and scissor state for this pipeline to be dynamic. So we need to set them in the command buffer before issuing our draw command. Okay. Now we have finally, wait, where's the command buffer begin? What the heck? VK command buffer begin info. Here we go. VK begin command buffer. Yeah, I just missed it. How did I miss that entire thing? There we go. All right, so we set up. Now we need to set up the main loop. Line of a frame. Image from the swap chain. Record a command buffer, which draws the scene onto that image. Submit recorded command buffer. Present the swap chain image. So we basically, and then we need to increment the swap chain image ourselves. Oh, hey, Colonel Will. Thanks for the raid. You might notice my energy is a bit low because we've been streaming for 7 hours. All I want to do is draw a triangle. Well, thanks for the raid. Everyone check out Colonel Will. Triangle sub 8 hours? Yes. Let's do it. I've got to finish this so you can go to bed, Fagart. Yeah, thank you, Raiders. We're not playing Factorio today. We are writing code. We are at 802 lines of code and we still don't have a triangle. Okay, so we can finally uncomment this, and then we can draw frame. Okay, GLW draw frame. Outline of a frame. Wait for the previous frame to finish. Acquire an image from the swap chain. Record a command buffer, which draws scene onto that image. Submit the recorded command buffer. Present the swap chain image. While we will expand the drawing function in a later chapter, for now this is the core of our render loop. Synchronization. According to design philosophy in Vulkan, is that synchronization of execution on the GPU is explicit. The order of operations is for us to define using various synchronization primitives, which tell the driver the order we want things to run in. This means that many Vulkan API calls, which start executing work on the GPU, are asynchronous. The functions will return before the operation is finished. In this chapter, there are a number of events that we need to order explicitly because they happen on the GPU, such as acquiring an image from the swap chain, executing commands that draw onto the acquired image, presenting that image to the screen for presentation, returning it to the swap chain. Each of these events is set in motion using a single function call, but all are executed asynchronously. The function calls will return before the operations are actually finished, and the order of execution is also undefined. That is unfortunate, because each of the operations depends on the previous one finishing. Thus, we need to explore which primitives we can use to achieve the desired ordering. Semaphores! Semaphore is used to add order between queue operations. Queue operations refer to the work we submit to a queue, either in a command buffer or from within a function, as we will see later. My brain is melting. Examples of queues are the graphics queue and the presentation queue. Semaphores are used both to order work inside the same queue and between different queues. There happen to be two kinds of semaphores in Vulkan, binary and timeline. Because only binary semaphores will be used in this tutorial, we will not discuss timeline semaphores. Further mention of the term semaphore exclusively refers to binary semaphores. A semaphore is either unsignaled or signaled. It begins life as unsignaled. The way we use a semaphore to order queue operations is by providing the same semaphore as a signal semaphore in one queue operation and as a wait semaphore in another queue operation. For an example, let's say we have a semaphore S and queue operations A and B that we want to execute in order. What we tell Vulkan is that the operation A will signal semaphore S when it finishes executing, and operation B will wait on semaphore S before it begins executing. Okay, I see. When operation A finishes, semaphore S will be hold on. Gosh, I'm getting ill. While operation B won't start until S is signaled. After operation B begins executing, semaphore S is automatically reset back to being unsignaled, allowing it to be used again. Okay, note that in this code snippet, both calls to vkQSubmit return immediately. Waiting only happens on the GPU. The CPU continues running without blocking. To make the CPU wait, we need a different synchronization primitive, which we will now describe. Fences!
So semaphores are purely on the GPU, and fences communicate between the CPU and GPU. Fence has a similar purpose, and that is used to synchronize execution, but it is only for ordering the execution on the CPU, otherwise known as the host. Simply put, if the host needs to know when the GPU has finished something, we use a fence. Similar to semaphores, fences are either in signal or unsignaled state. Whenever we submit work to execute, we can attach a fence to that work. When the work is finished, this fence will be signaled. Then we can make the host wait for the fence to be signaled, guaranteeing that the work has finished before the host continues. Concrete example is taking a screenshot. Say we have already done the necessary work on the GPU, now need to transfer the image from the GPU over to the host and then save the memory to a file. We have a command buffer, A, which executes the transfer, and fence F. We submit command buffer A with fence F, then immediately tell the host to wait for F to signal. This causes the host to block until command buffer A finishes execution. Thus we are safe to let the host save the file to disk as the memory transfer has completed. Okay, so it's like the same thing, but between CPU and GPU. Unlike the semaphore example, this example does block host execution. This means that host won't do anything except wait until execution is finished. For this case, we had to make sure that the transfer was complete before we could save the screenshot to disk. In general, it is preferable to not block the host unless necessary. We want to feed the GPU and the host with useful work to do. Waiting on fences to signal is not useful work. Thus, we prefer semaphores or other synchronization primitives not yet covered to synchronize our work. Fences must be reset manually to put them back into an unsignaled state. This is because fences are used to control the execution of the host, and so the host gets to decide when to reset the fence. Contrast this to semaphores, which are used to order work on the GPU without the host being involved. In summary, semaphores are used to specify the execution order of operations of the GPU, while fences are used to keep the CPU and GPU in sync with each other. Okay, so that's basically what I determined. Gosh, my throat hurts. I can't wait. I'm almost there. What to choose? So we have two synchronization primitives to use and conveniently two places to apply synchronization. Swap chain operations and waiting for the previous frame to finish. We want to use semaphores for swap chain operation because they happen on the GPU, thus we don't want to make the host wait around if we can help it. For waiting on the previous frame to finish, we want to use fences for the opposite reason, because we need the host to wait. This is so we don't draw more than one frame at a time. Because we re-record the command buffer every frame, we cannot record the next frame's work command buffer until the current frame is finished executing. And we don't want to overwrite the current contents of the command buffer while the GPU is using it. Creating synchronization objects. We have one semaphore to signal that an image has been acquired from the swap chain and is ready for rendering, another one to signal that the rendering is finished and presentation can happen, and a fence to make sure that only one frame is running at a time. Okay. Doesn't have any actual really required fields besides S-type. Future versions of the Vulkan API or extensions may add functionality for the flags and pnex parameters like it does for the other structures. Creating a fence requires filling in VK fence create info. Creating a semaphore and fence follows similar pattern.
Okay, semaphores and fence should be cleaned up at the end of the program. Waiting for the previous frame. At the start of the frame, we want to wait until the previous frame is finished so the command buffer and the semaphore is available to use. To do that, we call VK wait for fences. Device, fence count, in-flight fence. Wait all. Okay, true. Yep. 164 max. At the timeout? Yes. Anyway, for fences function takes an array of fences and waits on the host for either any or all the fences to be signaled before returning. VK true we pass here in the case we want to wait for all fences, but in the case a single one doesn't matter. Function also doesn't have also has a timeout parameter that was set to a maximum value of 64-bit unsigned integer, which effectively disables the timeout. After waiting, we need to manually reset the fence to the unsignaled state with the VK reset fences. Okay. Before we can proceed, there was a slight hiccup in our design. On the first frame, we call draw frame, which immediately waits on in-flight fence to be signaled. In-flight fence is only signaled after a frame is finished rendering. Since this is the first frame, there are no previous frames in which to signal the fence. Thus, VK wait for fences blocks indefinitely, waiting on something which will never happen. With the many solutions to this dilemma, there's a clever workaround built into the API. Create the fence in the signaled state so that the first call to VK wait for fences returns immediately, since the fence is already signaled. Ah. That is actually quite smart. Acquiring an image from the swap chain. Next thing we need to do in draw frame is acquire an image from the swap chain. Recall that the swap chain is an extension feature, so we must use a function with VK-KHR naming convention. Okay, so what's this doing? Device, swap chain, timeout, semaphore. Okay, so you have to use a semaphore for this. Image available semaphore. Fence, image index. Okay. Their parameter specifies a timeout of nanoseconds, using maximum value 64-bit, effectively disables it. The next two parameters specify synchronization objects that would be signaled when the presentation engine is finished using an image. That's the point in time where we can start drawing to it. If it's possible, it is possible to specify semaphore, fence, or both. We're going to use our image available semaphore for that purpose here. Okay, so that is the semaphore that is signaled when the image is ready. Yeah. The last parameter specifies a variable to output the index of the swap chain image that has become available. The index refers to a VK image in our swap chain images array. We're going to use that index to pick the VK frame buffer. According to the command buffer, we set flag a bit since we don't want to do anything special. We'll leave it as 0. Let's see what this is. VK reset. VK command buffer reset, release resources. The only thing. Okay, with a fully recorded command buffer, we can now submit it. Submitting the command buffer. Queue submission and synchronization is configured through parameters of VK submit info. Vulkan is much easier once you kill the worm, get poison grenades and red ammo. True. First three parameters specify which semaphores to wait on. Before execution begins, and in which stages of the pipeline to wait. Okay. We want to wait with writing colors to the image until it's available. So we're specifying the stage of the graphics pipeline that waits for the color attachment. That means that theoretically the implementation can already start executing a vertex shader and such while the image is not yet available. Each entry in the wait stages array corresponds to the semaphore with the same index and p-wait semaphores. Okay. Command buffer count 1. And the next two parameters, wait, can we just... Yeah, we can. Next two parameters specify which command buffers to actually submit for execution. We simply submit the single command buffer that we have. Okay, the signal semaphore count and p-signal semaphores parameters specify which semaphores to signal once the command buffers have finished execution. In our case, we're using the render finished semaphore for that purpose. Right, so this waits on image available and it signals render finished once the command buffer is finished executing. Hey, Maldor96, thank you for the 9 months. Vulkan, why are you calling upon the salamanders for help with graphics issues? Well, thanks for the...
Vulkan, why are you calling upon the salamanders for help with graphics issues?
Very good question. Thanks for the sub. I keep forgetting I have text-to-speech, so I keep reading it.
and then it reads it again. And then it's annoying. Okay, so VKQ submit. Okay. The function takes an array of VK submit info structures. Yep. Oh, so you can submit multiple command buffers at once. That's cool. The last parameter references an optional fence that will be signaled when the command buffer finishes execution. This allows us to know when it is safe for the command buffers to be reused. Thus, we want to give it in-flight fence. Now, in the next frame, the CPU will wait for this command buffer to finish executing before it records new commands into it. Subpass dependencies. Vulkan for what project? Learning. Yes, exactly. We're gonna have a sub 8 hour triangle, I swear. Actually, let's just see what happens if we run it now. Makes integer from a pointer without a cast. Triangle? Oh. Wowzers. Okay, well, let's Okay, remember that the subpass and a render pass automatically takes care of image layout transitions. These transitions are controlled by subpass dependencies, which specify memory and execution dependencies between subpasses. We have only a single subpass right now. The operations right before and right after this subpass also count as implicit subpasses. Okay, there are two built-in dependencies that take care of the transition at the start of the render pass and at the end of the render pass, but the former does not occur at the right time. It assumes that the transition occurs at the start of the pipeline, but we haven't acquired the image yet at that point. I don't know what this is saying. I'm not comprehending this. What distro is this? Fedora. Hold on, I'm reading this all again in my head. Here's wait stages for I think my brain is too fried to understand this. I'm just gonna skip it. I'm just gonna do what it's telling me. Editor Vim? No, it's Cocoon. Operations that should wait on this are in the color attachment stage and involve the writing of the color attachment. These settings will prevent the transition from happening until it's actually necessary and allowed. I'll have to start writing colors to it. Yeah, I'm gonna have to redo this whole section because I don't understand any of this. Presentation. The last step of drawing a frame is submitting the result back to the swap chain. Have it eventually show up on the screen. Presentation is configured through a VK present info KHR structure at the end of the draw frame function. Have you considered VK guide? It was mentioned, but I had already started Vulkan tutorial, so. First parameter specify which time photo window presentation can happen. Okay, that's what you said before is VK swap chain KHR. Next two parameters specify the swap chains to present images to and the index of the image for each swap chain. This almost always be a single one. Percent of P results. One last optional parameter called P results allows you to specify an array of VK result values to check for every individual swap chain. Presentation was successful. It's not necessary if you're only using a single swap chain because you can simply use the return value of the present function. Missed the request to present an image to the swap chain. We'll add error handling for both those in the next chapter because their failure does not necessarily mean that the program should terminate, unlike the functions we've seen so far. Okay. Triangle? Triangle! Triangle! It's beautiful! Sub 8-hour triangle. 7 hours, 39 minutes. 10 seconds, triangle. Ah. Oh, it's beautiful. But if we resize the, oh no, actually it's working. It's our triangle. I'll make it spin. Oh, I'm doing that tomorrow. I'm gonna need to put this down for a day or so. Make it a square. I need a vertex buffer for that. That's a whole nother shebang. I need a vertex buffer with a triangle strip. Well, actually, I guess I could do. Now you're having me tempted. I could just specify a fourth index in the shader. And then just set it to triangle strip and draw 4 vertices, and then we're good. I'm kind of tempted to try it, but look at all this trash. It's beautiful, but look at all these validation errors. Oh, I'm not actually getting the correct errors. Yeah, it does look different, doesn't it? It does look different from the SDL GPU triangle. Well, also it's the wrong... Just run? Yes, you did. Yeah, that does look different, huh? Vulkan is on the left and SDL GPU is on the right. That's interesting. I like the Vulkan one more. It looks more accurate. Oh, it's probably because we did the sRGB color space, isn't it? So I bet if we change this, we just remove this, just use the first one, it'll probably... No, actually, huh. Weird. But we have a triangle, baby! Okay, so how many lines of code is that triangle? That is 870 lines of code for one triangle. Oh yeah, plus the shaders, actually. Forgot about those. That is a crazy amount of code. Remember that all operations in draw frame are asynchronous. That means that when we exit the loop and main loop, drawing and presentation operations may still be going on. Here's our problem. We should wait for the logical device to finish operations before exiting main loop and destroying the window. Cool. Let's wait for operations. But we have all these validation errors, but I'm too tired to figure those out. A little over 900 lines of code later. Ha! I've saved 30 lines of code somehow, somewhere. That's actually a little worrying. Maybe that's why I'm getting those validation errors. Finally gotten to the stage of seeing something pop up on the screen. Bootstrapping a Vulkan program is definitely a lot of work, but the takeaway message is that Vulkan gives you an immense amount of control through its explicitness. I recommend you to take some time now to reread the code and build a mental model of the purpose of all the Vulkan objects in the program and how they relate to each other. We'll be building on top of that knowledge to extend the functionality of the program from this point on. The next chapter will expand the render loop to handle multiple frames in flight. How long will this take? I kind of want to finish this whole drawing a triangle thing, but I think I need to finish now because I'm tired. It's been almost 8 hours of reading and learning new things, and my voice is not happy, so I think we're gonna call it good here. But we have a triangle! We have a triangle! Triangle was the goal, indeed. It's beautiful! Hold on, I'm gonna make the window resizable. Whee! He's a big boy. Aw. Oh, so it is resizing it, but look, it's not resizing the frame buffer. The frame buffer is still the same size. So it's all jagged. Okay, well, that is a triangle. Oh gosh, OBS is not having a good time. That's weird. Huh. That was fascinating. All right, well, thanks y'all for joining me. That was crazy. We got our triangle though. I hope you learned something. I'll see you next time. We're gonna raid Brand Anarchy. He's playing Pi hard mode. Goodbye. One moment. This is not correct. I gave him a nice raid guard in the chat. And I'll see you later. Goodbye.